Okay, Dr. Kashinath, I welcome you for this talk, and I am very happy that you accepted our invitation for the session. And audience, I will just like to introduce Dr. Kashinath Oja. He is currently a postdoctoral research at a scholar at University of Oregon. He received his PhD in chemistry from Indian Institute of Technology in November 2016. Afterwards, he worked as postdoctoral fellow at Techno Israel Institute of Technology, Israel, and Leiden University, Netherlands. He holds expertise in fundamental electrochemistry, single crystal electrochemistry, electrocatalysis, and electrolyzers. His current research is on the understanding of various electrode-electrolyte interface and development of durable electrolyzers. He is a member of International Society of Electrochemistry. He has received many awards such as PBC Outstanding Postdoc Fellowship in Israel, MSCA, Seal of Excellence Award in Europe, DST Spire Faculty Award in India, and IC Travel Award by Young Electrochemist, etc. And Best Poster Award in that is a 5th Bangalore Nano Conference, and so on and so forth. So he's a excellent researcher. He's amongst us, and he will tell us about the electrolyte interface in electrifying the world. So I will request Dr. Kashinath just to start his session.
Thank you, Professor Pathak, for the introductions, and definitely it's a great pleasure for me to give a lecture on electrochemistry for the students, and I hope it will be enjoyable for everyone. Okay, let me share my screen. Yeah, hope you see my screen and hear me loudly. Okay, that's perfect. Yeah, as I said, so welcome to my lecture. So that's on electrode-electrolyte interface. It's mainly focused on electrochemistry, and that still I'll focus on this part, electrode-electrolyte interface, and which has a great role in electrifying the world. Today, it's a very important topic, depending on the current scenario in the world. Yeah, why we are interested so much on electrochemistry. Now, before going to that, I think we should know what is electrochemistry. And for the students, I'd say this is an important subject, and of course some people call it's a tool, but it's a way more than tool. It's a subject. So electrochemistry is a combination of chemical and electrostatics. So chemical in the means of they depends on thermodynamics. So basically you combine thermodynamics and electrostatics, and all together we call it electrochemistry. And so in the nature, if you look at those electrochemistry, or this combination of chemistry and chemical and electrostatics, they exist in nature itself. You probably heard of electric eels. So these are the animals. They can generate electricity, and not really a small amount. They a huge amount of electrical power they can generate. So they have thousands of cells in their body. That you can look at here. These thousands of cells, they can generate a small potential, and all together they generate a huge voltage. And it looks like each cell generates 150 millivolt, and where all together there's a 900 volt of electricity they can generate. And that they use them to communicate to each other, to defend themselves, and to generate to get their own food. Basically they use to as a prey, to kill the prey actually. And it's not only there. So if you know the cell membranes, so they generate a lot of electrochemical signals, and in particularly in neurons. So then those membranes, they are particular for ion transport. They are very selective semi-permeable membrane, and those ion transport happens when there is a potential changes, that because of the electrochemistry happening there. So there are a lot of the mechanism is there. They have a resting potential, then depolarizations. Basically, ions move one direction at sometimes other directions. So that gives you depolarization and repolarization. Basically, surface inside the cell become negative and sometimes positive. So these are all electrochemistry happening in nature, in natural systems there. Even you probably heard of lightning bolts. So they generate like a huge amount of potential. You see the lightnings, they're really high energy, and it's more than like 1 billion volts of electricity you can generate from each lightning. And they happen because those charged particles are accumulated in the cloud. So that's why that's happened. And yeah, it's a great experiment that done by Nikola Tesla, they artificially generate this lightning in the laboratory. So these are like natural things happens in the nature, but there are bigger, like more than bigger motivation to do electrochemistry, or like to understand electrochemistry more. So that's like motivation to do electrochemistry. So that's to me is right now is climate change. And it's happening now. It's not that like it's in future it's going to happen. It's happening now. And if you look at the events that happen throughout the world, so basically if you look at the wildfires, it's happened now in like most of the countries. And the floods, the more frequent floods, heat waves, you can see like the fish under the sea, they got burned due to those heat waves. More frequent hurricanes, and of course the icebergs are melting. So those things tells us that there is something we need to take care. That's basically we need to act on the climate change. And to me, it's the only way forward is electrochemistry, because to decarbonize the world, we need to electrify everything, and the electrochemistry is the way to electrify everything there. So here is my professor's quote. Actually, that's a very, I mean, I like those quotes, that the electrochemistry was always eternal promise, but nowadays it is more or less the only hope. So electrochemistry is the, I think, the only options we have. Now, if you look at the more like all the energy systems, they are available for us. So they are ranges of energy systems are there. But if you look at more carefully, so we currently use those energy systems. Now, this is the plot of energy system in energy density. So those are like volumetric energy density, and the others are this one is gravimetric energy density, basically by energy per volume and this energy per weight. Now, we want energy system which are really high in this corner. So in the graph, if it is this corner, it exits. So they are really good energy system for us. Okay, yeah. So if you look at those things, those are the main fossil fuel based energy system that we currently use, and they're not good for our for the world, and they leads to that climate change and everything. So we have to get rid of all these things, and then we have to come to something more green systems. That so if you look at the next available energy is there, but these are the very high energy density systems, so we can really look into nuclear fission and fusion. But those are technologically is not improved, or not really, the technology is not there available for everyone, and also it's not safe. There is a lot of safety issues are there. So the only options are there somewhere here. But if you look at those energy systems, and most of them are are electrochemical systems. So most of them having electrochemistry involved on those energy systems. And particularly if you look at hydrogen here, and that's a big role in the electrochemistry. And then the lower part of those graphs, so you can look at those energy, they are nice, but their energy density is very low. So we will not be able to use those systems because they are just not cost effective anymore. So if you look at the energy system, for sure we have to do more and more electrochemistry. So better we understand the electrochemistry more than doing it. And of course, the electrochemistry is not just doing a cyclic voltammogram or a 3 electrode measurement. There is a more than that. So cyclic voltammogram or 3 electrode measurements is a one way of doing the electrochemistry, but there are a lot of things. So electrochemistry to me, all the chemistry or the process happening at electrode electrolyte interface. So that's I call something like this. So electrode and electrolyte interface, whatever happening there, that's I call it electrochemistry. And it need not to be necessarily a solid liquid interface. We always think of that electrode means it's a solid, and it's not necessarily need to be. It can happen as a liquid interface as well. So but this is also electrochemistry, but this can happen at any interface. It's a water and organic interface. So all these reactions are all possible. All the electrochemistry can be done. So this is just an interfacial phenomena. So we all whatever in electrochemistry we talk about, and all happens right at the interface. That's I call this electrode electrolyte interface. Yeah, this is a one review paper that we published last year. So there we really comprehend like all the primers, particularly how to do and get like reproducible electrochemistry data. What are the standard procedures to do that, and where things can go wrong during the measurements, and of course different kind of measurements in the systems. One thing I need to mention that if you have any questions during the talk, please interrupt me. Otherwise, I'll just speak and then I don't realize like if something is going wrong or somebody missed something. Yeah, please interrupt me. That will be nice, I think. Yeah, so coming to that interface that I was talking, so let's say what happens at the interface. And if you look at those, the interface there, this is, let's say, the electrode surface, and and these are the electrolytes. And then it happens that there is some kind of deposition, new particle formation, new growth, nucleation. All this can happen, and all those things leads to a transfer of charge. So that basically we denote as a charge transfer resistance. So there has to be a resistance to transfer those electrons. And it's not only there, so if you have any reactions happening or at those interfaces, reactions means like there is a reactant molecule or species in the electrolyte or on the surface, and they get absorbed on the surface or doing a reaction, just simply reaction. Reactant comes in and go out as a product, and then you transfer a charge that can be an electron transferred to the molecule, or a molecule can leave a electron and that transfer to the electrode. So it can happen either way, but all these involves charge transfer. So that also requires there will be a resistance involved in there. And there is other process where the charge species are accumulating or like moving out from the surface. So there is like a distribution of charge species can happen when you apply a potential to the surface, and those accumulation or moving out of the charge leads to a change in the capacitance. That's we call a capacitor. That right there in the interface. So I'll more talk about later of this talk is this part. But yeah, let's see what we fundamentally we know. Yeah, so doing electrochemistry, I thought of these are also important because the one of the most important thing to do electrochemistry is where you do the electrochemistry. So the main apparatus we call cell, and that cell can be very different types depending on how you want to do the electrochemistry. And the most common use in the laboratory, they are like just a 3 electrode system where you can put 3 different electrodes. It can be a beaker, it can be a just a glass ball or like a beaker or something. You can put 3 electrodes there and electrolyte, and you can do all the electrochemistry you want, depending on how you want to do. Sometimes you put the electrode inside the liquid, and sometimes you put a electrode on the top of the electrolyte at like a hanging meniscus form. So it depends on experiment. And also there is the kind of geometry, we call it H cell, where like we can separate the electrodes in different compartment, and they are separated by a membrane. And those membranes are kind of a semi-permeable membranes, basically selective to one or another ions, because the ion has to transport through these compartments. Otherwise, you won't be able to drive the current at all. There is a device level electrochemistry. Those are called MEAs, basically membrane electrode assemblies. So those membrane electrode assembly, basically you have a electrodes both side, and in between you have a membrane, and we call it this membrane act as a electrolyte. So same as it's like here 2 electrodes, there are also 2 electrodes, and then electrolyte is there. Those membranes are like semi-permeable, so they are very selective to particular ions, and those ions, depending on which device, move one way to another. And talk about PEM electrolyzers or AEM electrolyzers. In PEM electrolyzers, protons moves through the membrane, while in AEM, it's anion, basically hydroxide, moves through the membrane. And there are also special configuration of cells depending on experiments. You can do in situ experiments like in situ Raman, IR, in situ X-ray diffraction or XPS, or X-ray absorption spectroscopy. So all depends what the experimental condition are. So, but these are like standard cell designs for various experiments involving electrochemistry. Let's move from there. So now I'll talk about the very important concepts in electrochemistry, and this is, I think, the most important for the students because they are like the conceptual part, and of course maybe interesting for others also. The first part is potentials in electrochemistry, and these potentials mean they are very confusing because they have many terms. And so particularly I'll talk about OCV, open circuit voltage or open circuit potential in electrochemistry. And this part particularly is in this talk is inspired by from the presentation from Geoff McClonie from Stanford. So he did a really nice job on that. But this part I presented from there because this is very particularly for students, and so they are very clear and very informative. And the later part, I'll of course talk about electrode electrolyte interface, and that involves double layer structure or Guy-Chapman theory. I'll talk about that in the later part. Let's talk about open circuit potential. So the open circuit potential is very informative for any electrochemical device. So basically, when we start doing an electrochemistry, we always look at the open circuit potential. What happens at open circuit potential, that informs a lot of things conceptually. But there are, like, if you go to the reference, all the different electrochemistry books, there are many ways and many names for this potential, so it's confusing. So if you look at those, they here like those books, so there basically it says the potential that we are measuring basically a electrostatic potential difference. And if you look at the Alan J. Bird's book, that's I think most famous electrochemistry book, that's basically the cell potential that like the energy required to drive a 1 coulomb of charge. So that's another definition. If you look at this book and by John Newman, there is it's a Gibbs free energy. Basically, this potential is the Gibbs free energy for 1 mole of species. or there are also like other definitions. It's a the potential is basically difference between the electrochemical potential of the electron at two contact points. So there are like a all different concept, and that's why this potential makes very confusing to others, although we don't understand fundamentally those things, but we only say like electrode potentials. I'll come there, like what are known in the electrochemistry. Now, before going there, so let me explain what is electrochemical potential. Now, electrochemical potentials, before going that, I'll explain this experiment that done in 1800 by Alexander Volta. Basically, this is called Volta pile. And so he produced a battery by sandwich, we call it sandwich battery, having a zinc with its zinc oxide layer, and then a silver with its oxide layer. So basically zinc and then zinc oxide, and then silver and silver oxide. They make a sandwich between two, in between, like put a electrolyte. So Volta use actually sodium chloride, and later people use KOH. But in any case, that's a electrolyte, and they are the two electrodes. Now, if you make the sandwich and then connect one electrode to another, with this basically there is electron flow happening. And with time, what you're going to see, that silver side, it's a silver side with a silver oxide, it's actually black. So it's basically kind of black. So the silver side become shiny, while the zinc is dissolving into the electrolyte. And that happens because of the electrochemical potential of the two species. So what happens here, silver is here is the silver oxide, basically silver plus, getting reduced and forming a silver metal, which is shiny, metallic silver, while zinc is getting oxidized and become zinc oxide, zinc ions, and that goes into electrolyte. So zinc is dissolving while silver becomes shiny. So that all depends on the electrochemical potential of the two species. Now, coming to those potentials, there are like so many different kind of potentials known in the literature. So these are, let's say, there is known like chemical potential, electrochemical potential, and then we call electrode potential. There are the surface potential, inner potential or galvanic potential, outer potential. Those are all the terms are there. But what we care, we know the chemical potential, electrochemical potential, electrode potential. They are mostly chemical properties, depends on chemical properties. So basically they are thermodynamic property of the species. While the surface potential, inner potential or outer potential, they are coming from electrostatics. Now, if you look at the notations, so bit careful about notations, because next onward, all the slides, I'm going to deal with all these notations. They're going to, sometimes it may be confusing. Now, electrochemical potential is the summation, is the combination of chemical potential of the species and their electrostatic potential as well. So basically, if it is a charged species, so that's the chemical potential plus the electrostatic potential into the total charge. The Z is a number of valency of the species, and F is the total charge of a 1 mole 1 mole of charge species. So that basically, if you multiply the total valency with the charge, and then that is the total charge, and then yeah, that's a electrostatic potential of the. Then if you add both two, you get a electrochemical potential. Now this is a very important equation to remember of any charged species having its electrochemical potential. Any charge or any species, it not need to be charged. So the question is, like, if it is a neutral species, what going to be the electrochemical potential for the neutral species? Let's say a metal atom. What going to its atom? It's a neutral metal atom. What going to be a chemical potential? But if you look at this equation, so this is the valency of the charged species, and that valency goes to 0. So basically the electrostatic part is nullified, and then you end up with a chemical potential. So basically electrochemical potential of a neutral species will be the chemical potential of it. And then if you talk about interface where all the electrochemistry happen, where all the reactions happens, and there, so this is the most important relation where the total electrochemical potential of all the species in a particular phase has to be same the total electrochemical potential of the other species in the other phase. Now this has to be same when it is in equilibrium. So when you have an interface, they always come to an equilibrium, and then you have this total electrochemical potential of the species has to be same in both the phases. Now this is, if you look at like how electrochemical system defined. So here we took a very simple electrochemical system. Let's talk about two metals. Two metals, they are in contact. So the metal A and metal B, they are in contact each other. So let's say you make a contact between them, and then what going to happen? So both the metal has a different number of electrons. They are different elements. So the electrons will be, the energy of the electrons will be different in both the metals. So, but in any case, if you have a contact between those two metals, then there will be electron flow from one to another to balance or to get the equilibrium. And if you look at here, so at equilibrium, the electrons, the electrochemical potential of the electron in metal A and electrochemical potential of the metal B has to be same. So that is the an equilibrium state electrochemical potential of electron in both the phase. Now, if that rules is valid, then basically the electrochemical potential is A equals to electrochemical potential of the electron in B. Now, if you remember this relation, the first relation, then just put if you put it there instead of this electrochemical potential, if I put it in chemical potential and electrostatic potential, so we just put it there in both the side, and the minus sign comes because it's electron, so it has a -1 charge. So it's in place of Z, it's a -1. That's why the minus sign comes. But if you just rearrange those, then the total electrostatic potential difference in both the metal at the interface is equals to the chemical potential difference. So that means, so if we measure if we put a voltmeter, if we connect a voltmeter both the side of these two metals, then what we're going to measure? So we're going to measure the chemical potential difference between two phases of the two metals. But in reality, we generally measure 0 volt. Nothing happens. Now that's because in actually we should measure a electrochemical potential difference, but that is 0 because in the voltmeter, the both side the wire is made of same material. Let's say it's copper, so it's same material. Let's put it there. So if we connect a voltmeter to these two metal systems, so then you look we add one connector, basically one metal here, that's a D, and then another connector, another metal here, C. Let's talk about those are two different. Then we work similarly as that interface, AB interface. So we now have DA interface, then AB interface, and then BC interface. Now, if you do the same math that I did the previous slide, basically we get a electrostatic potential difference at equilibrium at those three interfaces, and they are simply chemical potential difference. And if you calculate the total electrochemical potential difference, in the all three interface, basically you add all three and then rearrange it, and they actually can cancel out each other. So you measure a 0. Now, you think about, instead of two metals, if you have a
May I
one,
interrupt,
yeah,
Dr.
yeah,
Kashina?
please.
So, but what about the kinetic aspects? Like, so, as soon as you touch them, the electrons will
Mhm.
flow and,
Yeah.
you achieve equilibrium. And then, so what about the kinetic aspects? You understand my question, right?
Yeah. So like,
Yeah.
yeah, how fast those electrons
Yeah,
moving, like depending on
and then would we be able to measure at all? Like, if in optical spectroscopy, we do time resolves, we do
Mhm.
it on a nanosecond scale and
Mhm.
all. But here also something similar would be happening, right?
No, this is here actually, this at this stage there is no kinetics involved, because there is
Okay,
no electron. They are just like, these electron transfers are
okay,
really small amount, because they
okay,
are just
okay,
equilibrating their system. There is not kinetics involved here.
okay, okay. Thank you.
I mean, there is kinetics will be involved if there is, let's say, you add another system here. Instead of, let's say, B, you add a B plus C, some two different things, and then it makes more complicated, because if there is reaction between, or anything between happening between B and C, that then it's create a big problem. But they are more difficult to understand, difficult to, like, yeah, just it's not straightforward as like simply two metals.
Okay, thank you.
Yeah. So let's talk about, if instead of two metals, let's say one metal and then one electrolyte, which normally, if you see in electrochemistry or any electrode electrolyte interface, you have a metal and an electrolyte. Now, if I, let's say, I treat both them as A and B, and then in the electrolyte, from the B, it's, let's say, B ion is going to the electrolyte, or B ions were in electrolyte, they are depositing on B. So basically dissolutions happens, or depositions can happen. Now in both cases, so B is a solid, basically the electrode go back and forth to a B ions which are in A medium, and then generate a electron which in the B. And then same way we can calculate, we can talk about the electrochemical potentials of each species. So here the electrochemical potential of B in solid, electrochemical potential of the B ions in A, and then electrochemical potential of electron in B here. Now that is very simple. Now let's say in a realistic electrochemical cell, because that's like a half interface in electrochemistry. And in real electrochemistry, you always have a two interface. Basically, you have to complete a circuit where the charges are flowing circularly. Not, you can't drive a half reaction in any conditions. There will be always a complementary another half reactions going on in real electrochemical system. Now let's talk about the real system, and let's say this is a medium having electrolyte, and then we have a two different metals, two different one A and another B, and same from one is from A to the like it goes as ion into the electrolyte as A plus, and there is a B minus ion is depositing on B. So same way we can write those half reactions back and forth, and we can write those electrochemical potential of the all the species. Now overall potential of the whole cell will be summation of will be summation of the electrochemical potential in B, and then electrochemical potential of in A. So one is going out and one is depositing. That's why like, oh sorry, the difference between two electrochemical potential in the two system. So that's in B minus A. Now if you rearrange those equation, Those equation basically electrochemical potential of the electron in A. If you get this equals to will be this minus this one. And if you rearrange those and this one as well, and then put it here, so you end up with this. And then if you look at those, these are neutral species, B and A. Those are neutral species, and neutral species electrochemical potential can be a chemical potential, as I said earlier. So this is electrochemical potential, and of the neutral species will be chemical potential. And this, the ions, the electrochemical potential of the ions in the solution, we can write as chemical potential minus electrostatic potential of the solvent. So that we can write it here. And same way, this becomes chemical potential, and also same way we can write this is also chemical potential, and this one is chemical potential plus electrostatic potential of the solvent. And if you as this is the same solvent, so basically the electrostatic potential is cancelled out, and then what you see is you all are chemical potential. There is no electrochemical potential involved here. So in a real electrochemical system, what we measure at open circuit is at equilibrium, we measure a difference in the chemical potential of all the species involved in the system. So that we can say like a delta mu. That's basically whatever reactions happening, whatever the systems are there, we are measuring only difference in the chemical potential of all the species, not any electrochemical potential. So that's what we measure at OCB. So once OCB is a typical definition, it says when you put an electrode into an electrolyte, there is an equilibrium. To reach that equilibrium, there is some charge compensation happens, and that leads to some potential, some potential difference, and that potential we call it OCB, and that is basically comes from the chemical potential differences. Yeah, if that's like a particular example for lithium-ion batteries. So basically, in lithium-ion batteries, the lithium ion goes into intercalate into a one of the electrode, and then another electrode is basically lithium. There, it's lithium come to the it become lithium ions. It comes to the solvent or electrolyte. So one is generating lithium ion, and another is intercalating. And as both are same ions, and if you do the same old exercise, and then basically we get a electrochemical potential difference, that's basically chemical potential difference of lithium in both the different metals. So that's so in any intercalation batteries, particularly let's say lithium ion batteries, the electrolyte concentration doesn't change the OCV, open circuit voltage. So if you change the electrolyte concentration, that doesn't change the OCB. While in other cases, here this is basically depends on chemical potential of all the species. So basically, if you change the ionic strength or electrolyte concentrations, so then you're going to change this. So then you can see those OCB is changing. But in batteries, lithium-ion batteries, you won't be able to see those things. I think that's like a quite good explanation on OCB. That's concept wise. But there is another concept I'll talk about, this double layer structure. Now, double layer structure is like whenever you put an electrode into an electrolyte, there is a double layer structure forming, and that's more than 100 years old theory. I'll explain. I try to explain much clear way so that the student can get the information right. So let's say that you put an electrode inside an electrolyte having ions and solvent. So there is a mixture of ion and solvent solution. So depending on the charge of the electrode, there will be a layering of ions will happen. So basically, if your electrode is positively charged, so your anions will come close to the electrode, and then there will be a distribution of ions. If it is a negative charge, your cations will come close. And of course, when you put an electrode into the electrolyte, there will be a solvent layer on the electrode. Now, in this initial solvent layers, we call it inner Helmholtz layer. And sometimes, depending on the ions or species in the electrolytes, they can specifically adsorb on the electrode. So particularly, basically, anion, they bind chemically with the electrodes. Now, those layerings, it's called as a double layer because we kind of two layer formations. So one is, we call it Helmholtz layer. There is a solvent layer, inner Helmholtz layer, and then there is an ion layer, the opposite to the charge of the electrode, and that ion layer we call it outer Helmholtz layer. And then there is, depending on charge, there is a distribution of ions that we call diffuse layer, or it's another name is Guy-Chapman layer. And then there will be a bulk electrolyte, bulk concentration that. So, but in that particular interface, you have a distribution of ions, and there will be a gradient, and those distributions we call it double layer. And where we see it, every electrochemical system we see those double layer. Not even electrochemical systems. You probably heard of colloidal system, particle dispersants, anything. If you have an ions charged species and a dispersion colloidal things, they are always a double layer structure forming. Even in the soils, soil particles, they're like, we put fertilizers. The fertilizers are basically different ions, and we put a lot of water. So then it's still, there is also a double layer structure forming with the soil particles. Now let's go in more details. So there is, before going in details, I want to explain that this point, we call it point of zero charge or potential of zero charge. We call it PGC. And that's the one important parameter for any electrodes. That's like intrinsic parameter. So we call it point of zero charge, particularly for colloidal systems, dispersions, where solid particles are dispersed in an electrolyte or in a solution having some charge species. So in that case, the ion also goes a distribution at the interface, and that can be monitored basically via pH. So we call at particular pH, the net charge of those particles will be zero. Net charge on those particles will be zero at particular pH. So on that pH, we call it point of zero charge. But for electrodes, if you put it in electrolyte, and on those electrodes, if you apply a certain potential, and that potential, the net charge on the surface will be zero. So that potential is called potential of zero charge. I think it's clear to understand. If you don't understand, let me know. Yeah, coming back to the double layer structures, still you have two layers of ion layering formations, and overall capacitance of those interface, we call it two capacitor in series. One is Helmholtz layer capacitance, another is Guy-Chapman layer capacitance. Now those capacitance are in series, so there will be total capacitance of the interface is equals to 1 by C equals to 1 by CH plus 1 by CGC. Now that's a series connection of two capacitor. Now this theory is given by Guy-Chapman. They're like 100 years old theory. You can look at the year 1910 and 1913, and they give the expression equation for the capacitance to calculate what is the capacitance and this diffuse layer. So you can actually calculate the capacitance if you know the potential, and if you know the concentration of ions present in the electrolyte. So basically, if you simulate this equation, then you will get a capacitance with respect to potential, and you get a U-shaped curve. And at the potential of zero charge, when E equals to EPGC, then you get a minimum value of the Guy-Chapman capacitance. And that point, we call it potential of zero charge. So basically, this is a classical method to find a potential of zero charge of an electrode. And how we can find, but because we can change the potential and we can change the concentration of the electrolyte, and we measure the capacitance value. And then if wherever we see a minimum in the curve, a capacitance curve, and that point we can say that is a potential of zero charge. And it's not just a theory, and experimentally, and people have found those capacitance minima. So this is a very standard classical measurements, 1947 by Graham, that on marker electrode. So they got at different electrolyte concentrations, they got a capacitance minimum right at the PGC. Same for silver electrode and gold electrode, and then all they found the capacitance minima at different electrolyte concentration. Basically, if you go very low electrolyte concentration, then only you will be able to see these minima. And why we should go for low electrolyte concentration? Now, if you look at those equations here, once your the concentration is very low, and they, at that time you see a minima, because you don't see this 1 by ch will be much, ch will be much higher than 1 by ch will be kind of negligible. So total capacitance of the system will be equals to the Guy-Chapman capacitance. So because once you make it a low concentration, then this GC is a smaller value, but CH is much higher. So that goes like a negligible. But at high concentration, so these become super high, and then we only see the Helmholtz layer capacitance. Now, so all these cases, 1 millimolar ionic strength was really low enough to find a capacitance minimum. But in electrochemistry, you know which metal is most used in electrochemistry? It's probably platinum. And platinum is like, everybody used platinum as an electrode and a catalyst, whatever. But as a platinum, we never saw those capacitance minima. And those capacitance minima tells you about how this diffuse layer is arranging in the double layer structure, how their double layer structure is. So from those capacitance, we can actually tell about the double layer structure of the electrode. But in case of platinum, we never really found those minima. So that was a challenge, and people tried, like it's more than 50 years, and nobody found double layer capacitance of the or diffuse layer capacitance of the platinum, or basically potential of zero charge for the platinum. And nobody found, and they tried the measurements. They instead of a minimum in the capacitance curve, they found a peak in the curve. And that is a bit surprising, because if you go low concentration, you should see a minimum in the capacitance curve right at the potential of zero charge. Although there are other techniques to detect the potential of zero charge, they found it 0.3 volt by other techniques. Those techniques are also standard, but they never found using the classical Guy-Chapman theory. So I started doing experiment on that. So this is a single crystal electrochemistry. So we have an electrode, we have the single crystals of platinum, and we cut particular surface. For our experiment, it was 111 surface. So we get the only surface that is having a 111 structure of the platinum atom. And we do electrochemistry in a meniscus configuration with the electrolyte, where only that cut surface is exposed to the electrolyte. The other surfaces are not really touching the electrolyte at all. So whatever electrochemistry happening, whatever the ion interactions are happening, they are happening only at those surface, only that particular surface, not the other surfaces. So this is typical single crystal electrochemistry people do. And in most of the cases, we use
So
that
Dr.
hanging.
Kashinath,
Yeah,
how do you like grow this? Like, do you grow these crystals, or how do you
yeah.
obtain?
So we can grow in the lab. We can also buy. There are company we can buy those, but we grow those in lab. So we basically melt the platinum, high pure platinum metal, melt it and slowly cool down
Like
to room temperature.
zone refining,
Yeah,
sort of. Okay.
that's yeah. If you
Uh,
do that, then it crystallizes, and then you have a different facets are like.
so
Um,
what is the guarantee that this particular facet will be there exposed?
Oh, we know from the crystallographic, that's called like a crystallographic orientations. If you look at even you can look at in ACM or
X-ray.
in microscope, then you can see like how the different facets are
No,
really oriented.
that I understand, but every time you obtain the same facet,
Oh yeah, so
or
we use we when we cut those orientations, particular sites, we use laser to really we use laser and reflection method to get the accuracy of that surface. So if our accuracy goes like 0.001 degree in angle, that's basically a bit deviated from the surface, but we maintain those the angle to when we cut those surface, and
so
that is
so
very
you grow
important.
you grow a crystal by zone refining, and then you cut it using a laser, right?
No, I mean
Laser
we cut
guided
by
beam.
no, not laser cutting. We cut using the polishing with a
Acha.
diamond, and
Diamond
then
polishing.
yeah, that polishing we do we tune the polishing, and in between we check the how much angle we are getting using that laser. So
Hmm. Okay.
that's like yeah, that's how we get those surface
And then
perfect.
you characterize using HRTEM or STEM to get
Yeah,
the facets. STM.
we do actually STM to look
Yeah,
at the
yeah.
how
Okay,
surface.
okay.
And for platinum, we have a very fundamental electrochemistry, and if you do normal electrochemistry also, we'll be able to say, oh, which this surface is this facet, not this one. So
Okay.
because each
Thank you.
facet has a very
Oh,
particular
okay, okay, okay.
electrochemical
Yeah.
signature.
Ah,
Yeah, so yeah,
okay.
so
Thanks.
I don't think I have something to show, but yeah, this is, let's say this one is very typical signature electrochemistry. I call it capacitance curve, or a cyclic voltammogram, you can call it. So this is a very typical for platinum 111. So if you have another facet, you won't get this one.
Okay,
So if
okay.
you have an even small degree of like error, small degree, then you end up with a two peak over here and here. Those are hydrogen adsorption peak at the step sites. I'll come there in between. But if you do not get 111, you also don't get those peaks as well. This peak intensity defines,
Okay.
like tells you how accurate your surface is. So they
Okay.
generally has to be like more than kind of three times to this HUPD. So this HUPD charge, let's say it's like a 700 and kind of 700 or 750, and those goes like 2000. Yeah, this
Okay.
kind of thing. Yeah. So basically, this is a well characterized system and well defined structure of the electrodes. And we do electrochemistry in meniscus form configuration. And then we look into the capacitance curve of the platinum 111. And probably if you don't know, let me tell you, like these different regions, we already like it's already known in the literature, and we characterize those. This region, call it hydrogen at UPD, or hydrogen adsorption region. Basically, if you in this way, if you scan, that is like hydrogen is desorbing from the surface, and if you go this way, that's like hydrogen is adsorbing on the surface. And then if you go more negative, then you start hydrogen evolution reactions. So before hydrogen evolution reactions, you deposit a lot of hydrogen on the surface. And on the other hand, this high potential region is a OH adsorption region. So here you adsorb OH, while you scan back, you desorb OH. And in the middle, this region, there is actually no specific adsorptions happening. That's we call a typical double layer region, where only ions are charging, discharging happening. Basically, ion goes close to the surface, and then while discharging, ion goes away from the surface. So basically, this is a charging, discharging box, and we call it double layer. Now, ideally, if we do a low ionic strength measurements, we should see a minimum in this capacitance curve right here. And if we need to tune a little bit the pH of the electrolyte, because the potential PGC is independent of pH. But if you do measurement with respect to RHE, so everything shifts, but the PGC doesn't shift. So in that case, our pH is 3 and 4, and that time our pH, like the experimental PGC, the known PGC should lie right in between here. And so therefore, at low ionic strength, we should see a capacitance minimum right at this place. But instead of that, we did 1 millimolar, we don't see a minimum. Very strange. And then I went even like much lower electrolyte concentration. That's like a micromolar concentration, 10 times lower. And probably in the world, nobody did that, that low electrolyte concentration measurements. And I went like 100 micromolar electrolyte concentration. And that time I see a minimum in the capacitance curve. And as I increase the ionic strength a little bit, and then my capacitance goes higher and higher. And at some point, I don't see that minimum anymore. And this is exactly Gui-Chapman theory tells them. If you go really high concentrations, you don't see the minimum at all. If you remember the capacitance curve for mercury, and at some high concentration, you don't see the
But
minimum at all.
Dr. Kashinath, what about
Yeah.
the minima at 0.45, between 0.4 and 0.45? What
Oh,
about
yeah,
the minima
this
there?
is so. Yeah, you talk about this one. This is not a capacitance minute. There is
Okay.
specific adsorption happening right here. I told you the hydrogen adsorption
Okay.
region.
Okay.
So this region is a specific adsorption happening, and that overlaps with the double layer region. So there it's creating a minima, but this is not actually minima in the capacitance region. This is a mix of capacitance and
Okay.
and specific adsorption. Same as here, but those are not really minima to consider. But this is a minima which is following with ionic strength, and that exactly follow the Gui-Chapman theory. It's a very exciting result. So there we confirm that this potential is corresponding to potential of zero charge of the platinum, and it's exactly matching the potential of zero charge which is derived from other methods by other groups. And if we do more studies on like different ions, different concentration, different conditions, what we found is those regions actually depends on cation water interactions, and those regions depends on anion water interactions. And there is like those two are like merging together at high concentration, those like moving together, and then at high concentration they are, instead of a minima, you see a peak, because those two are like merging together. And there is a clear kind of schematic. So if you have a negative charge on the surface, let's say on platinum, then you have a solvent molecules, particularly here is water, which is hydrogen is towards the surface. And once hydrogen is towards the surface, basically oxygen is upward, then this attracts cations to come closer. And that leads to a change in the capacitance curve. So that once cation goes closer to the surface, then leads to a capacitance, like increase in the capacitance. So that leads to a peak. While if your surface is positively charged, then your hydrogen is up, the oxygen is down, because positive charge, it attracts negative. So oxygen is down and hydrogen up. And then those hydrogen attracts anions to interact with them. And then again, the ions come closer, then also again, you see a increase in the capacitance. And capacitance is nothing big, because that's a like the charge divided by your distance. So your charge is coming closer, so your capacitance is going up. And in between, you have a kind of zero charge condition where your surface doesn't have a charge. That's like exactly potential of zero charge condition. And that time, water remains flat. And once it is flat, it doesn't really interact with the ions so strongly. And that time you see a minimum in the capacitance curve. Yeah, again, let's moving forward. If we look at this Guy-Chapman capacitance, that's we have in a different, basically it relate to the square root of concentration of the ions present in the solution or electrolyte. And also I have the data which have a different electrolyte concentration. So basically I can look at those capacitance values, and also I can calculate theoretically the capacitance values at those particular concentrations. And I can match like how theoretical value is matching with my experimental data. And that's called Parcel-Joubel plot. So we plot experimental capacitance inverse versus calculated capacitance inverse. Now, if both experimental and calculated capacitance are same, that time you're going to have a linear curve having a slope of 1. And if you remember the first experimental data on double layer structure, that's Graham on Marcari by Graham. And that was quite ideal. You have a slope of 0.95. It's very close to 1. Perfect. People believe it and it's really nice. But if you look at silver and gold, they are deviated from 1 bit significantly. Also, people didn't realize that this is a deviation or the theory is not perfect until we find our platinum capacitance and we plot that. And if you see from 1 to it's like a huge deviation. And that is because the ions are more and more ions are coming close to the electrode, close to platinum, and that leads to very high capacitance. Now this slope is much smaller because my experimental capacitance is much higher than the calculated capacitance. Now, if experimental is higher, capacitance is higher because more and more ions are coming close to the surface. Now that leads basically earlier, if I explain you rightly, that the double layer structure, you have an ion and you have a counter ion depending on the charge, counter ion on in the outer Helmholtz layer, and then distribution of your all the ions in the diffuse layer. And in case of platinum, all those ions come close to the surface. And that means you do not have really a diffuse layer at all. So that's what happening. So the ions are moving much closer and there is like a very little diffuse layer or almost not there. That's like a typical double layer structure on platinum. And probably that's why platinum is so active active and use catalyst in many cases.
So Dr. Kashinath, so this was possible because of your lower concentration of electrolyte, or this?
No, even at high concentration also, all the ions come closer to the surface. Now, how do we understand? Because I did all the experiment at low concentration. At low concentration, you should have those ions are distributed a bit far, and then we should see the diffuse layer much prominent that at high concentration.
Okay.
So Dr. Kashi, what was the concentration of electrolyte?
I use 100 micromolar.
Okay, but generally for electrochemical process, we are going for the millimolar concentration.
Yeah, generally we do like 0.1 molar, 0.5 molar, 1 molar, 2 molar, maybe as low as we go like 10 millimolar, 20 millimolar. Generally in normal experiments, we generally stay some 100 millimolar concentration in normal electrochemistry when we do in the laboratory. Nobody does electrochemistry such a low concentration. And
Okay.
there is a challenge to do that because
Kashinath,
yeah,
I'm Costa from BRC.
Yeah.
With very nice result. Just one question. Is it true for the other surfaces also?
yes, I'm coming to that. So if you look at this plot, Parseval-Joubel slopes, basically we call it Parseval-Joubel plot. If you look at, so the only the experimental data matches theoretically only for Mercury. Okay, so Mercury is really well, like Mercury system is very ideal, and it's exactly matches with Guy-Chapman theory, and that is perfect. That's a 100-year-old theory, electrochemistry main theory, and it's perfect. People believe it. It's nice. But if you look at silver and gold, they are also deviated from the slope 1. So that means the some kind of ion association or like accumulation happening to some extent on gold and silver as well. But the platinum, it's too much, like one of the extreme. But on in case of gold, it also happening some to some level. Yeah.
Yeah, again, if you check the theory versus the experimental result plot for Mercury, it is generic. I mean, it's Mercury. Again,
Yeah.
for silver and gold, it is again 111 surface, right? Equivalently for
Yeah.
platinum, it is 111 surface.
No. It's a Mercury is also it's a 111, like it's the because Mercury that time it's used. Mercury is liquid, and you can get really pure surface, and in case of that time it's Mercury was possible because liquids the surface will remain flat, and in on the top electrolyte is there. But for that time, like this is done at 1970 1940s, and that time platinum, silver, gold, you won't be able to generate really high oriented this crystal facet at all. And so these are done really later. And yeah, Mercury is still the same surface, same thing. Actually, I'll show you that it doesn't matter which surface is there. So it will not depend on the structure of the electrode. It will not depend. Let me show you.
What was the surface area of the electrode?
Oh, surface area is normalized. So it will not matter because in all cases, surface area is normalized.
No, but what was it in the experiment? Because you had to, this is again the single crystal one you're talking about, these ones?
Mine,
so what-
mine was like 0.08 centimeter square, I think. Yeah.
0.08 centimeter square. But then, you know, how do you, it's a challenge to measure it, right? Because it is usually not a symmetrical, you know, surface, right? It is not like a perfect square or a perfect, you know, a circle.
No, we do calculate the surface area from the electrochemical signal. So you can calculate surface area from those adsorption areas, So they are, so basically if I have a structure, later I can, so like each atom, so hydrogen adsorption region, so on each atom, so hydrogen like adsorb on each atom. On that case, so if you just calculate the total charge here, that will tell you how many hydrogen is adsorbed on the platinum surface. And from there, you can calculate how much area of your platinum is there. So that's a, we call it electrochemical surface area.
Electrochemically active surface. Okay.
Yeah.
Okay.
Yeah.
Thanks.
Yeah. And single crystals, they are really good in as normal surface area, like a geometric surface area, as electrochemical surface area, because each atom is really active. They are very flat surface, so nothing is wrong there in single crystal electrochemistry.
So Dr. Kostov, your question is answered. Is it answered?
Yeah, I'll show that the structure of the system will not affect those measurements. I'll show the.
Well, actually, his question was apart from the structure of the system, it was mainly about the other metals. I mean, so
yeah, I explained that
gold and
this
yeah,
is,
okay. So
I think that answer my that your question.
Yeah. So Dr. Kostov, Dr. Bhattacharya, I mean, is it? Can we continue? Is it fine? Are you satisfied?
Sure. Please continue.
Yeah.
No
Yeah.
problem.
Please.
Yeah. Okay. So So I did even more measurements on that. And what I did is, let's say these are depends on the ions. So the ions are accumulating. So if you change the ions, what happens there? And we did change a lot of the ions, but the slope doesn't change much. It's almost like kind of same. They are all error range. So the slope doesn't change. And what we see is in different ions, the minimum in the capacitance curve, they are changing in the directions. So if you have a smaller ion like cation, let's say lithium ion, and then your minima shifts like lower potential. And if you have a bigger ion, cesium ion, then it's shift to higher potential. Same way, if you bigger anions, and that time also it shifts lower potential, and smaller cation or smaller anion, then it shifts to higher potential. So that leads some kind of effect is there, that that ion is interacting to the surface. And that interactions, although we believe that interactions happen through the water structure on the surface, and that leads to some kind of additional capacitor, and which gives really high capacitance as in the double layer structure. And that's why we are getting much higher capacitance than theoretical expectations. And then we derive this model. So in normal double layer structure, that's like the known double layer structure, known theory, that they are like, you have a electrode and electrolyte, you have some ion distributions over the distance there, and that's we call Guy-Chapman-Stern theory. And basically we have a two capacitor in series. That's the textbook theory now. Now what we observe is there is some kind of ion surface interactions are there, and that leads to additional capacitor, and that leads to all the ions move closer to the surface. So there is accumulation of ions happening. It's happening on platinum, it's happening on gold, and to some extent silver. And mercury, of course, that's not interactions are there, because the ions are not interacting to mercury. That's one of the reason we believe there is no water structure involved on mercury, and that's why there is no interactions. But in our case, so we see additional capacitors that is parallel to the Guy-Chapman capacitors. So this is our new model, and we calculated according to the capacitance, and we found exactly similar to theory. And this came as a very big news in all of the world. It's appear in phys.org. The century-old electrochemistry law needs to be updated. And I hope it will be in like next version of all the textbooks. It will be included in the textbooks. Yeah, as I showed you that ions doesn't change the Parseval slope. Let's see what's changed. So I did different surface. So here, and on platinum, I cannot do different surface measurements, because in the double layer region that I showed you in the CV of the platinum 111, on the other faceted, we don't find a clear double layer region. That's always overlap with specific adsorption region. So then we won't be able to get an ideal data. So we don't do that. And then for gold, it is very ideal material to do the double layer measurements on different surface, because they have a clear double layer regions. So I did that. I did 3 different gold surfaces and look at their Parseval slope, and they are exactly same. They are not changing with the surface. I think this answers the question, how about the surface of the material, structure of the material. And also it will change the pH, and pH also doesn't change the slope, even for other surfaces as well. So the thing is, I showed it doesn't depend on the ions, doesn't depend on the pH, and doesn't depend on the nature of the surface. So let's look at the equation again. So this is a Guy-Chapman theory equation, and it depends right at PGC. When E equals to EPGC, this term is 0, or 1. This term is 1, and then only the Guy-Chapman capacitance is proportional to this. And if you look at carefully, Guy-Chapman capacitance is inversely so proportional to 1 by square root temperature. Now if we do the different temperature measurements, and that has to be linear with 1 by square root T. And we did that. So what we did is, this is the capacitance at different temperature, and it's plotted 1 by square root T. So this is a calculated value at 1 millimolar concentration. Basically, this is a linear line having a slope. And but if you look at the platinum double layer capacitance at all those different temperature, it's not linear at all. So it's going down, it should go down further, but instead of going further, it's at high temperature, it's go up again. So that means there is some non-linearity there, and that suggests there's some additional capacitors that we add in the model, and that leads to the non-linearity, not really a Guy-Chapman equation. And also we look at the Parseval-Joubel slope in different temperature, and if you look at, as we increase the temperature, our slope is increasing. So that means, so that slope, basic slope increasing means that we have a smaller capacitance value, experimental capacitance value than the calculated one. Now, why it's become smaller capacitance value? And at high temperature, those interactions of ion between the surface is like disturbing that. We are disturbing those interactions, so no more ion accumulation is happening, so the slope is increasing. I think I'll skip this system now because it's already too many time. Yeah. Do we have time?
We have one more speaker. It is almost how much time do you need? How much more time do you need?
I mean, if I need, so then another 10 minutes.
I think with Dr. Kaustav, is it okay if we start 10 minutes later?
Yeah, please go ahead, no problem.
Yeah, okay, Dr. Kashinath.
Yeah, so then what we did is looking at the double layer structure, we change the surface. We change the surface means we introduce step sides, and we want to see how those step sides affect those double layer capacitance of the platinum. Now, this is a like typical step platinum crystal, and you have a like these we call terraces, and then this position we call step. So we have a step and terrace, and then we can change the width of the terrace depending on the crystal. So we have different crystals having this n value indicate the number of terrace atoms. So basically 111, we do not have step at all. So that's like an infinity number of terrace atoms. So we do not have step. And then 15, 15, 14. So the number of terrace atom is 29. So basically we have a 29 atom width of the terrace. And then 10 and 4. So basically we increase number of steps in the surface. And then look at the double layer capacitance. Now, if you look at the capacitance value, right, this place is the potential of zero charge, where we look at the Guy-Chapman capacitance. Now, if you look at here, we don't change the capacitance much. It's almost same, but only thing, the minimum bit shifting towards lower potential. Same as here. This is two different electrolyte measurements, but they are both basically same. Now, what we did is we add foreign atoms, we deposit foreign atoms on these step sides. So once we added silver atom on these step sides, another we added ruthenium on the step sides. And this is a very controlled depositions. The electrochemistry wise, it's a very controlled depositions. You, from the electrochemical signals, you will be able to say how many atoms of silver or ruthenium you deposited and where exactly deposited. It's all very informative in the electrochemical signature. So this region is again the HUPD region, hydrogen adsorption region, and this basically this side, this peak is hydrogen adsorption on the step platinum sides. Now this is 553, and the step platinum single crystal, and if you add silver on the step sides, then you basically block those step sides, so you don't adsorb uh, hydrogen there, so that peak is like minimized, like you don't see the peak anymore. But rest of the HUPD region remains same, because rest of the HUPD region is coming from the terrace atom, hydrogen absorption on the terrace atom. So terraces are fine, only step sides are blocked. Same as for ruthenium as well. We also see when we deposit ruthenium, similar things. But there are what happens if you deposit silver and ruthenium, and choosing those two elements, also there was a reason behind it, we'll explain later. And I did with a different step surfaces. And what is interesting is when you deposit ruthenium on the step sides, then your double layer capacitance is going up, and your minimum in the capacitance curve also shifting to our high. But if you deposit silver on the step sides, so your double layer capacitance is going lower and lower, and your minima shifts to the lower potential. So that's a very interesting thing, because in one case you are increasing the double layer capacitance, in other case you are decreasing the double layer capacitance. Now that's, I'll not explain these experiments, but the only thing is, so what happens on silver is not really active at all. So silver doesn't dissociate water there, and the ruthenium is really active. So ruthenium does dissociate water. So once ruthenium dissociate water, so the OH minus adsorb on these sides. So they are negatively charged, so they become a negative charge sites. And once those negative charge sites, then on the other hand, in case of silver, as it doesn't really dissociate water, so that's like remain as positively charged side. They are not neutralized. So that we did this experiment to check if really they are positive or negative or not. And as those are positively charged, and they are somehow influence the water structure on the terrace, and that leads to much smaller double layer capacitance. While they are negatively charged and OH is there, and OH is really coordinating with water. So the water structure on the terrace, they are really become more solid, and that's why you have much more ion interaction on the terrace happen, and your capacitance really goes high. Yeah, take home message. So we probably learn about open circuit potential, and then we talk about Gui-Chapman capacitance of platinum. We talk about the new model for the double layer structure, and also we learn about how we can tune the double layer capacitance using step sides and foreign atoms. With that, I would like to acknowledge all my supervisors throughout my research career, my PhD supervisor, Ashok Ganguly, and my postdoc in Israel, David Eisenberg, in Netherlands, Mark Copper, and currently my supervisor, Susanne Butcher. And of course, thanks to all my collaborators, current and previous lab colleagues, and of course the funding agency and institute. With that, I would like to thank you all, and any questions, I'll be happy to take those.
Yeah, I mean, I think in the interest of time, we can skip the questions because Dr. Bhattacharya is there waiting. So, but I think Dr. Kashinath would be very happy to take questions. You can, on a personal basis, if you have some questions, you can, route them through me or through directly to Dr. Kashinath.
Yeah, definitely.
Yeah. So I think it was a very, very educational talk. There were many, there's some basic concepts that, students don't understand. So that were, made clear, because many of the students are actually lost in the, electrochemistry, they get lost in the language of equations. So, they see long equations and they are just like, what is this? So half of them don't, they get, what should I say, ticked off, or they don't, really want to delve into it. But it was a very good explanation. So I thank Dr. Kashinath for this time, and for delivering such a nice lecture. But, before we introduce the next speaker, I'll just talk a bit about the seminar series, the series that we are conducting today. So the Department of Chemistry, Biochemistry and Forensic Sciences at Amity University, Haryana. So we have been conducting a seminar series on contemporary research endeavors for the last 3 years. And this is particularly aimed to benefit the students of MSc Applied Chemistry. And for them, it is a 1-credit course. Okay, so they have to write
Dr.
reports.
Anirban, I will correct you here. It is a 1-credit course for all PG students in our department, Biochemistry and Forensic Science also.
Okay,
So
madam.
in that way, we want them to expose for the research going on in the on the world level. So now you can continue.
Yeah, thank you, madam. So that was our head of the department, madam, Professor Seema Pathak. So, continuing our endeavors, we are extremely fortunate today that we have amongst us Dr. Kashinath Ojha, who just delivered a very wonderful talk on electrochemistry, basics of electrochemistry, as well as the contemporary research that is going on in electrochemistry. And Dr. Ojha is currently at University of Oregon in USA. And the next speaker that we have is Dr. Kaustav Bhattacharya. So he is actually at the Bhabha Atomic Research Center, Mumbai, and he is an extremely accomplished young researcher in the field of catalysis. And Professor Seema Pathak will introduce Dr. Bhattacharya more. Meanwhile, again, thank you, Dr. Ojha, for the kind talk. And
Thank you for the invitation, and it's really nice to talk all those fundamentals in front of students. Really, it's
and faculty too. I mean, everybody. I think everybody benefited from it, and thank you. And we would be looking forward to more interactions in the future.
Definitely, if there is a question, definitely you can reach out to me directly or through Professor Das. I'll be happy to answer those.
Yeah. Thank you.
Thank you so much.
Yeah. Thank you.
Thank you, Dr. Anirban, and thank you, Dr. Kashinath. Actually, it was a very informative talk, and I am delighted because I left electrochemistry a decade back, and it was revision for me. So thank you very much for being here, and I do hope that you'll be keep on doing this. Suddenly sitting here, an idea came up in my mind, Dr. Anirban, why not we can do a seminar on electrochemistry only? In which we can call experts from different regions, and what is the work on the electrochemistry. We can have a deep sense of electrochemistry, and because of this online forum, we can have advantage of persons who are not here in India. So thank you, Dr. Kashinath, and you are the first person who is spoken on electrochemistry. So definitely you accept our invitation right now, that whenever we are going to conduct a seminar, you will be our resource person, right?
Of course, I'll look forward to it. Yeah.
And
thank you so much.
I welcome from my core of my heart, Dr. Kaustav. And Dr. Kaustav, I'm listening from long back that you are coming to deliver a talk to our department, but anyhow, it was not possible because of your commitment at Bhabha Research Institute. I'm very proud that you accepted our invitation and you spared your time for our students. Definitely, I feel like that my students will be benefited, and each person who are coming to my department, I fix them as my co-partners for future also. So I wish that we'll continue this journey together. So Dr. Kaustav, I will not take too much of time. Please embark on your knowledgeable session, and thank you very much.
Yeah, Dr. Kaustav, are you there?
Yeah, I'm there.
I must congratulate Dr. Anirban for getting such a wonderful speakers. Thank you very much, Dr. Anirban.
Thank you.
And please, you keep on doing your contributions to department so that we can reach laureals. Thank you.
Thank you. Yeah, your screen is visible.
Yeah. So Good afternoon, everyone. Myself, I am Dr. K. Bhattacharya. I am from Chemistry Division, Bhabha Atomic Research Center. Basically, I am from India only, and I am from Mumbai. We work in, the main station around Bhabha is Mankut, and we know, like if we are coming to Mumbai, there are lots of good foods. It's a nice city. You all can visit Mumbai and have the laurels of Mumbai. So this is my lab here in Mumbai. Here in BRC. This lab is called, this one is we call it as modular lab or mod lab. Used to be one of the longest building in Asia once upon a time. Now it is not. It is almost around 1 kilometer long. So you need not do any jogging or anything in the morning. If you just walk to my lab, it is good enough for your morning workout. Okay, so coming back. So I'll be delivering a talk on the basics of XPS, and it's more tuned for the students. I'll be showing least lower amount of the results, but more about the basics of XPS spectroscopy. Okay, so starting with the molecular processes. If we go down the ladder, we have the different energy levels for the motion, like the rotational motion. Then comes the vibrational motion. Then comes the electronic excitation, and then comes the bond breaking or the ionization reaction. So today we'll be speaking in the regime of the bond ionization energy, where usually from the regime from ultraviolet to X-ray to the gamma rays, it is used for the process of ionization. So today's talk will be mainly on X-rays. So we'll be utilizing the X-rays for the ionization process and checking the energy of that electron through the detector. So that's basically my X-ray photoelectron spectroscopy, correct? And if we generically divide the different spectroscopies according to their energy levels, we can check, like there can be a translational movement, there can be a rotational movement, there can be a vibrational, electronic, and nuclear movements according to the energy levels. So presently the translational energy levels are like, we don't have exactly a spectroscopy for translational apart from the time of flight mass spectroscopy, which utilizes mainly the kinetic energy of the molecules. For the rotational, we have microwave spectroscopy. For vibrational, we have infrared and Raman. For electronic, there are a plethora of spectroscopies. It depends upon whether we are using the absorption or the emission type of spectroscopies, or we are using a sort of X-ray spectroscopies where we, as I was telling, either where we either ionize the molecule, or we need not ionize the molecule even, or we can have electronic EPR type of spectroscopy. Equivalently, in the nuclear spectroscopy, we can have the gamma spectroscopy, and NMR, then Rutherford backscattering, PNS, like positron annihilation spectroscopy, so on and so forth. So initially, the electromagnetics, if we check the electromagnetic spectrum from the lower to the higher side, if we go, so today we'll be dealing with somewhere this regime, where we'll be working with mainly the soft X-rays to ionize the materials, and also a bit of ultraviolet rays to ionize the materials. Okay, so generically we know that X-ray is produced if an electron is knocked from the one of the core shells, and then another electron jumps from the upper shell and comes to that particular shell. It leads to a particular X-ray, and that X-ray is pertinent, or that the elemental property of that particular element, which is giving me the X-ray. So so basically, before we start saying like particular K alpha or particular L alpha, which is unique for a particular element, which is the elemental property of a particular element, so we need to understand like from which orbital it is coming and how much energy it is giving. So so once we have the X-ray, we need to understand how this X-ray, or how these X-ray source interacts with the matter. So there can be different types of interaction. First interaction is that it can have just a transmission without any amount of changing in the energy. So what we called as Thomson scattering. Then it can have a generic scattering, where we if the energy changes, that if the X-ray which is coming to interact with the matter, there's a different energy of the X-ray that comes out, that is called a Compton scattering. Now that Compton scattering, if it is having a lower energy, it is a Compton scattering. If it is having a higher energy, it is called an inverse Compton scattering. Apart from that, it can have an photoelectric absorption, like where it can absorb the X-ray and produce an electron, which is called photoelectric absorption. And apart from that, for the very high energy X-rays, it can have an pair production where it produces both a positive and a negative charge together. So, but the pair production is usually often higher, much higher energy. It's not with the soft X-rays. It's always with the hard X-rays of the higher energy of the order of minimum of 1.02 MeV region. So, and now if we go with the different elements with the Z value of the element, and if we see the what energy we are using as an X-ray for that particular element, the means absorption coefficient varies. So these absorption coefficient for these different phenomena has their own probabilities because these are probabilistic parts. So we check that initially the Thomson scattering, then comes the energy of the Compton scattering, and in between somewhere here is my photoelectric absorption part. So we should be utilizing such a material or such elements X-ray where we get the maximum amount of photoelectric absorption, because we'll be utilizing this photoelectric absorption to the maximum extent to produce and get the X-ray photoelectron spectroscopy part. Okay, so the Thomson scattering usually that depends upon the Z by 4 by e to the power cube rule. The photoelectric part, as we all know, so once you put an X-ray, if the energy is higher than the phi value of the element, the electron gets ejected from the surface, and we this electron we will be utilizing in the present study. Compton effect I already have understood. Okay, so so for the XPS model, it is using the photoelectric effect, which earned Einstein the Nobel Prize in 1921. And the photoelectric and the XPS was developed by Kai Sekban, who in the year 1981 used as an analytical tool for using this photoelectric effect to calculate the energy of the different orbital levels exactly and perfectly. So that led to an instrument which gave him the Nobel Prize in the year 1981. So what really happens? So if we put an X-ray on the element, the core electron gets ejected. Okay, so now if one core electron gets ejected, this process, the kinetic energy of this electron is measured by the detector. That gives me the model for XPS, that is X-ray photoelectron spectroscopy. Now, equivalently, what can happen is that once this electron gets ejected, this hole that is present, it can relax a bit, and another electron from the higher model can come and jump here. So that releases the extra amount of energy. That extra amount of energy, if it releases another electron from the same orbital, it is called an Auger electron. Or if it doesn't release an electron and it only fluoresces, the process is called X-ray fluorescence. And if it ejects another electron, it is a secondary electron. So that secondary electron is called the Auger electron. So any XPS process will always be having the AES process, that is Auger electron emission, along with the X-ray photoelectron emission. And equivalently, it can also the competitive route will also be having a X-ray fluorescence part. So so if we put so we can check the system like this. We have put some X-rays here. The electron is being ejected from the from the vacuum. This photoelectron is being produced, and the energy of this photoelectron, or the kinetic energy of this photoelectron, is being measured by the detector. So we have so my detector is mainly measuring the kinetic energy of this photoelectron. So this kinetic energy of this photoelectron will be equal to the energy of the X-ray that I have emitted minus the binding energy of the electron, that is the energy in which it was binded, minus the photoelectric work function, that is the energy that is required from the Fermi level to the vacuum level, that is the work function of the material, which is particular of a particular element. So it depends, this kinetic energy will be equivalent to the energy of the X-ray source minus the binding energy of the material minus the work function of the material. So, and similarly, as I have said, For the Auger, there can be the competitive process will always be having an Auger emission or an X-ray photon emission. So there is this comparative probability of the XRF, that is X-ray fluorescence, where it emits and fluorescence on its. So for the higher elements, the X-ray fluorescence is more, and for the low Z elements, the Auger electron emission is more. And there's a crossover around the mass number of 35. So up till the mass number of 35, we get a good amount of Auger electron emission. But post 35, the Auger electron probability diminishes. And for very high Z material, there is very less amount of Auger emission. However, for them, the X-ray fluorescence emission probability is very high. So for any high Z element, the X-ray fluorescence will be a nicer tool to check the concentration. So if we have that system where we have a core level, we have a Fermi level, and we have the vacuum level. Now, if we equivalently have the same instrument, the vacuum means the phi level, that is the level of vacuum level of this element of the material, and the vacuum level of the spectrometer should be merged. And equivalently, this kinetic energy will mostly be dependent on the phi, that is work function of the spectrometer, rather than on the work function of the sample. So this is constant. So the binding energy of the material will directly depend upon the kinetic energy. So if we experimentally, we are measuring the kinetic energy of the material, and we know the source energy. So more, and this is almost constant for a spectroscope, means for the particular spectroscopic material, or for the particular spectroscope. So we can exactly find out the binding energy of the material from this equation. So X-ray photoelectron spectroscopy, initially it was known as electron spectroscopy for ESCA, electron spectroscopy for chemical analysis. And if my source is not an X-ray, if my ionizing source is an ultraviolet source, it is called an ultraviolet photoelectron spectroscopy. So with this ultraviolet photoelectron spectroscopy, we can measure the kinetic energy, or we can measure exactly the energy of the valence electrons rather than the core electrons. We always measure the binding energy or the kinetic energy of the core electrons from the X-ray photoelectron spectroscopy, whereas UPS gives me the binding energy or the kinetic energy of the valence electrons. These two together, that is the X-ray photoelectron spectroscopy and the ultraviolet photoelectron spectroscopy together, is called photoemission spectroscopy, or we call it as PES. So basically what we have, to make the long story short, we have an X-ray source which falls on the sample. It ejects a photoelectron. The kinetic energy of this photoelectron is measured by the detector, and this kinetic energy of this photoelectron is correlated with the binding energy of the system. So we get the binding energy of this system. So, so as we have found out the binding energy of the system. So what we can identify from this X-ray photoelectrons, we can identify the particular element, like which element is being produced, because every element has its own particular energy of electron being ejected from the shell. We can understand the comparative relative composition of the surface, and we can have the equivalently the valence band structure. We can have the basically what we get is the density of states. That is that we get the every density of states related to that element. By density of states, like we can get the energy of the particular orbital of each element with the energy limit we have with the source. Whatever source we have utilized, within the regime of that source energy, we can find almost all the band structures or all the orbital structures that are being released. Okay, so now we almost always hear a word that X-ray photoelectron spectroscopy is a surface technique. So why it's a surface technique? Let us clarify that one first. So it is a system where we use X-ray as a source. So the depth of the X-ray source, or the X-ray source, the penetration depth of the X-ray source is infinite, because the X-ray source as such is a chargeless and massless entity. So the penetration depth of it is infinite. It can travel to any extent. Obviously, it depends upon the energy of the X-ray. Therefore, the XPS, being a surface sensitive, is not dependent upon the penetration depth of the X-ray, but it depends upon the ejection of the electron. So basically what we are doing, we are ejecting out, or we are ionizing an electron, and the electron that can be ionized can be done only from a certain amount of the surface. And if we check the bulk electrons, or the electrons that are present in the bulk system, it's very tough to eject them out. And also it's very tough to exactly get the kinetic energy of that bulk electrons. So this system is more of sensitive to getting the electrons almost up to like 5 to 7 nanometer depth of the system. So that's the reason XPS is usually called surface sensitive technique. Okay, so now we come to a thing called Fermi level referencing. So once we if we have a material, we all know that if we look back to the last figure, so this is my Fermi level, right? Energy of my Fermi level. So if I can know exactly the energy of my Fermi level, I can reference either the material with it, or if I can reference exactly my Fermi level energy, I can exactly find out my valence band potential, because the next energy level after the Fermi level will be my valence band. So this EV we cannot find out from the XPS, but definitely we can find out the Fermi level. So as we can find out the Fermi level, we can definitely find out the valence band potential also, or the valence band energy from the XPS. Okay, so in order to do that, so we need to understand that in the Fermi zone very strongly. Once we can take the X-ray photoelectron spectroscopy in the Fermi regime. So basically for a 0 degree Kelvin, for an element or for a material, the Fermi level should be 0, but it is not so because we are not dealing at 0 degree Kelvin. So every Fermi regime or Fermi energy will be having a particular energy value. We need to understand what is the energy value for that, and then we can calculate the other values. So we can do the referencing by knowing the what is the value at that of the Fermi age at that particular room temperature. We can find that, we can make that to ground zero, and then we can calculate. That is one way of referencing the material. Okay, so now we basically have, if we have referenced the material with the Fermi, so now what are the different ideals in which we can, the things depends. So first of all, we can think of that a material, which is a generic material, it can have a surface charge also. So its overall binding energy will be depending on the energy that is given by the X-ray, plus the kinetic energy of the electron that is given, the phi, that is the work function of the spectroscope now, and also it will depend upon the surface charge. So if my surface is not having a 0 charge as the Fermi charge, that if my EF is not 0, then my surface is having a charge. So that charge will also definitely have a part to play in the binding energy, that we need to know. So if the surface is already charged, then we need to deduct that surface charge from the binding energy to get the exact binding energy of the material. So for that, we usually always take the carbon 1s as the as one of the as the internal calibrating agent. So we get the 1s at almost 284.5 electron volt. We need to calibrate that. Initially, we need to calibrate that instrument with either gold or with copper or with silver, any one of the two. And once we know that instrument is properly calibrated, perfectly calibrated, then we can definitely substantiate that the carbon 1s will be having a value of 284.5 or 284.5 eV. And now if that particular carbon 1s is having a higher charge than 284.5 eV, we can understand the surface charge from that, and we need to reduce that surface charge to get the exact binding energy for the elements that are concerned in the system. Okay, so now we need to understand, like if the material is in a different electrochemical regime, or if it is bonded with different materials, so then how these binding energy shifts come, from where do they come? So the primary question, we can pose it like this, like for example, we have a material like sodium. If it is bonded with fluoride, chloride, iodide, like that, if we have a different entity of materials together, then how does its binding energy is being affected? So two things usually the binding energy is being affected. One is the charge of the electron and the nucleus that we need to understand, like what is the density of charge there. And equivalently, the binding energy also depends upon, as we have ejected an electron, so it also depends upon the electron-electron repulsion. So basically, as we are putting out one electron, so it will be depending upon the electron-electron repulsion and the electron nucleus attraction. These are the two primary forces in which will be playing the major effects for calculating the binding energy. So how much the nucleus attracts the electron for which it is to be ejected, that's play a very strong role to calculate the binding energy. And equivalently, as we are ejecting one electron out, suppose that how much the electron-electron repulsion part is also there, that also plays a equivalent role for finding out the binding energy. So these are the two primary factors which play a stronger role for finding out the binding energy shifts to be calculated. So if we check like if we check the elemental shifts, what we get is that like I'm coming to the how we get them, but in order to understand that, like for example, if we check iron, cobalt, nickel, copper, and zinc with their XPS value for the 2p32, we see that for the higher amount of nuclear charge, that is, if the N value increases, the binding energy increases. And equivalently, so therefore, we can understand that from going from, so and equivalently, the particular energy for the particular orbital of an element is constant, and the delta E of the splitting parameter is also constant for that particular element. So for iron, for example, if we are getting 707, we usually say the iron is in the form of iron 0. Equivalently, if we get it from cobalt, it is in the form of elemental state. We say cobalt is in the form of cobalt 0. And if we get the nickel, equivalently, 853 is for the metallic nickel, 933 is for the cobalt. Similarly, so we will be getting the energies of the almost all the orbitals. So so whichever is the maximum energy I'll get, I mean the probability of the orbital which is maximum, that we take into picture. The other orbitals, if we don't get, or if it is not affected by somebody else, then we need to use some other orbitals also. So we check all the orbitals. Okay, so now the elemental shifts. Now we check like for the copper 2p, for the nickel 2p, we have a definite shift. You can see that for the copper and the nickel, as the elements are different, the binding energy of these peaks are also completely different. And if we get copper in, if we get usually the binding energy of the electron in this regime, we usually say for copper 2p, and equivalent for the nickel, it is coming to a higher binding energy. So binding energy determination. So we do the binding energy determination. So basically, as I have said, one thing we need to understand is that for the XPS system, we are not that much concerned with the valence electrons. We are more concerned with the core electrons, and as these core electrons are ejected, so okay. First thing first. So if we want to play the quantum mechanical model here, so the electron, once it is ionized, it goes to a continuum, correct? So once electron goes to the continuum, you cannot play the quantum mechanical rules exactly there. So for the calculation of the states, or calculation of the each state, so it is known as the final state binding. So what we consider is that once the electron is ejected, it is out of that this free electron regime. It's after that it's a complete continuum. So we say that whatever we get from the XPS is its final state. So whatever the binding energies are calculated, are upon this final state model, upon this final state configuration. So we say that there's a certain approximation here by the Koopman's binding energy, where we have, that is, we have ejected one electron and we have exactly n-1 electrons there. And that n-1 electron, what is exactly the final state energy there? And we use you use basically the Hartree-Fock orbital energy to calculate this particular energy for the orbitals, and that orbital energy are being utilized for the XPS measurement. So the binding energy chemical shifts will be basically depending upon the electrostatic point charge model. So it will be depending upon initially the charge of the atom or the charge of the nucleus with which the reference is there, then the charge of the particular ion or the particular thing or the particular weighted charge of the particular electron, and equivalently it will also depend upon the potential or the potential field applied on that particular ionic charge or the particular electron which is surrounding that charge. So all three of these together will lead to the calculation of the binding energy as a sum of it. Okay. So now the equivalently the chemical shift or the electronegativity effects. For example, if we are checking the carbon, so carbon 2p, so if the carbon is added, like say for example, the carbon is bounded with an hydroxyl group, or the carbon is bounded with an hydrogen group, or the carbon is bounded with a nitrogen group. So the electrons surrounding that carbon are different. So obviously, if we go by the last equation, so this part definitely plays a stronger role, where the potential around the carbon will be different. So equivalently, the binding energy for that particular carbon with a different surrounding charge will be different. So that would lead us to understand that how a carbon is being bonded to different entity, and how its point charge differs for that, and that leads to exactly the change in the binding energy of the carbon. And if we can understand that change in the binding energy of the carbon, and if we compare with the particular carbon, then we can understand how its order of the electronegativity charge and the binding changes. Similarly, so now the core level shifts. The position of the orbitals in the atom is sensitive to the particular chemical environment of that particular atom. So we are taking in the gas phase. So so if we have if I have, for example, say a different amount of fluorine around the silica, so like silicon fluoride, SiF2, SiF3, SiF4, where the oxidation state of the silica changes and also the amount of fluorine changes. So first of all, XPS doesn't see it as doesn't see the moiety or doesn't see the entity as a compound. XPS always sees the entity as a particular element. So wherever we will be getting the peaks for Si and fluorine together. And as the core level shift changes, like for the particular charge or the particular oxidation state of the silica alters, so equivalently the drawing out of the electron from that particular silica will be different. So its binding energy will shift, and equivalently we can exactly say, like from what is the exact oxidation state or exact the value of the binding energy of the silica to the charge that is being bounded. So for example, if we check for a hydrocarbon, like for a CH or for CC, we usually get a binding energy of say 285.0. Whereas if we check for an alcohol or an ether, we almost get a 1.5 eV shift. If it is bound to fluorine, we get a stronger shift. Like for example, you almost get a 2.8 eV or almost 3 eV shift. Or again, if it is bounded to a doubly bond carbonyl group or a doubly bond nitrogen group or a triply bond nitrogen group, we have a different shift. So accordingly, we can say like how the carbon is bounded to a particular group, and also we can find the qualitatively what is the population, and we can say how much amount of that particular group is present. Okay, so now we come to the peak splitting. So what happens is that, for example, we always we know that we have the 4 basic quantum numbers, that is the principal quantum number, azimuthal quantum number, magnetic quantum number, and the spin quantum number. So always if we have we usually have a LS coupling, that is L is always coupled with the S to have 2 different energies of the L. So it can have an L plus S value and an L minus S value. That's what we call as Russell's undersplitting. And in the XPS, we can exactly find out the splitting parameter or the splitting parameter for the particular Russell's undersplitting or the spin orbital splitting value. And that particular value of the splitting parameter is internal property of an element. So from that, we can also identify that particular element. And also we can find out the total population of these different orbital splitting parameters together. So for example, if we have say the S orbital, so S orbital is usually having a value L equal to 0. So either it can have a L plus S or L minus S value will be either plus or, so as we are having a mod value, so any the orbital value S won't be splitted. So any S orbital, whether it be 1s, 2s, 3s, 4s, whatever it is, so we don't get a splitted S orbital. We get a complete, means we get a single peak for an S orbital. Equivalently, for the P orbital, we have an L value equal to 1 and a spin value of half. So we'll be having two different peaks of P3/2 and P half. And the energy, if we go by the binding energy, the 2p3/2 will be having lower binding energy and 2p half will be having higher binding energy always. And equivalently, the difference in this binding energy, what I mean to say is that difference in this energy, that is LS splitting parameter, like for copper 2p, we have this splitting parameter as 19.8 eV. And if this 19.8, even if we get 2 peaks of 2p3/2 and 2p half, and we don't get an delta E of 19.8 eV, then it is not copper. Then it can be in some different element, though it may come in the same region. Equivalently, for the d orbital, we will be having 2 different peaks of 3d 5/2 and 3d 3/2. And obviously, that will also be having a particular splitting parameter. And for the F, we can understand it will be having F 7/2 and F 5/2. Similarly, we can also find out the population for a particular splitted orbital. Like for a particular orbital, we know that the population is given by 2j plus 1. That is, if we have the population ratio for a p orbital, that will be equivalent to 3/2 into 2, that is 3 plus 1, 4, 4/2, that is 1:2. So p 3/2 by p half, the area ratio should always be 2:1. If the area ratio is not 2:1, then then there is something else to it. Then we should understand that there is something more to it to understand. But the area ratio for that particular element should be in 2:1, and also the splitting parameter should be fixed for that particular element. Then only we can consider it as that element we are considering. Equivalently, for the d orbital, the area ratio we can understand 2j plus 1 for both of them. So that will be 6/4. That is, they should be in the ratio of 3:2. And for the F 7/2 by F 5/2 ratio should be in the ratio of 4/3. Okay, so now we come to the other different peaks, what we get apart from the generic peaks, what we usually should think of getting, but we end up in every spectroscopy, we end up in getting some extra peaks, what we call as spooky peaks, or what we call as some extra definite or other peaks we get. In XPS also we get some several definite different peaks. So first of all, let us understand what are satellite peaks. So as I have told, in the X-ray system and in the XPS system, my source was X-ray source. And so basically the X-ray source should be of a particular element. For XPS, we use as a lab source as either aluminum K alpha, magnesium K alpha, silver L alpha. These are usually the sources that we use. So, if we are not using a monochromatic source, we are usually using a dual anode source. And if you're using a dual anode source, I mean, we know that there are two anodes side by side with a separator, and equivalently with the excitation of the high voltage, though there is a separator, still there is a small amount of magnesium impurity that's coming into picture along with the aluminum impurity. So that gives rise to another peak that we call as satellite peak. So basically satellite peaks are because of the impurity in the X-ray or impurity in the source that we get. So if you're using the aluminum K alpha source, along with the aluminum K alpha, there is a very, very small or negligible amount of magnesium K alpha that also comes into picture. For that, we get some certain peaks that those peaks are called, we call them as satellite peaks. Okay, so next comes what we call them as plasmon loss peaks. So, equivalently, if anyone has any question in between, you can just kindly ask me. Please go ahead. So the plasmon loss peaks are like, so again, like if we have a surface metal which are having different plasmons on that, so the energy of that, exactly the energy of that electron that is being ejected is more than that of the electron that is being present. So that also needs to be taken into account. So we say that there's an extra amount of plasmonic part into that electron, and from that, if we can calculate exactly the plasmonic part from that electron, we can understand different parameters of the different elements from different directions from that particular photoelectron. And now we come to the shake-up peaks or the shakedown peaks. Shake-up peaks or shakedown peaks are usually found out from the materials which are not metals, which are basically compounds. For example, so what we are thinking of always is that the electron that is ejected is basically a core electron. Now, what can so happen is that particular core electron from where it is being ejected, that can have some overlap. So, for example, let us say copper oxide. Say, for example, now the electron that is ejected from the copper can have that core electron from where that is being ejected, that 2p core from where that copper electron is being ejected, that can have an overlap with the valence electron of the oxygen. So there is some contribution of that oxygen valence electron by coupling with that copper together. That leads to giving me an extra peak that is called a shake-up peak. So that can lead for the energy to being enhanced. That is, that coupling of that energy can lead to an enhanced energy of that, which we call a shake up, or what it can happen is that it can lower down the energy a bit, but we call it as shake down. So for example, as I was telling, for copper, so in the if I check copper metal, it's a clean. So if I get a 2p 3/2 and 2p half peaks, but for a copper oxide, what happens is that this oxygen now it has got some contribution or some overlap with that particular 2p orbital of that copper metal. That leads to another one or two peaks, what we call them as either satellite peaks or shake-up peaks. And equivalently, so and if we can understand like how this energy of these satellite peaks varies with the system, we can definitely say from in the how these contributions from the overlap integrals, that is how these overlap of the different orbitals with that particular orbital of copper differs or changes along with the energy. Okay, then we come to the multiplet splitting. So multiplet splitting is something like that, where like similarly what happens is that we for example, this is very seen often for materials like ceria, manganese, etc., where what happens, the ceria, I mean the original orbital of the ceria, once the electron is taken away, so that orbital is not exactly a particular orbital, but it is being a small amount of energy contribution is there from other orbitals also present. That leads, what happens is that leads to the splitting of that peak. So we should get at least, I mean, for a ceria, like for a 2p, as we have understood from the LS splitting, we should get 2 peaks, that is 2p half and 2p 3/2. But in origin, we don't get 2 peaks, we get 4 peaks. What we get is that 2p 3/2 and 2p half themselves are also split in energy by a small amount. That's what we called as multiplet splitting. Usually the multiplet splitting are because of that non-degeneracy of that particular orbital, happening of the non-degeneracy of that particular orbital. That can be for different or varying reasons. And if we can understand why this non-degeneracy is being created, we can understand how this non-degeneracy affect in the particular material. Like for example, if it's an oxide, or if it's a sulfide, or if it's a nitride, how this non-degeneracy of the ceria can affect the bonding structure. Okay, so now then we come to the quantitative analysis by an XPS tool. So whatever the peak we get, the intensity of that peak depends upon several factors. The intensity of the peak depends, first of all, we know intensity of the peaks will definitely depend upon the population, that is total number of atoms or the total number of electrons that are being present and are being injected. Equivalently, it depends upon the photoelectric cross section, like what is the probability of that particular orbital from which the electron can be ejected. Similarly, it also depends upon the other tools like the detector efficiency. Then it depends upon the flux of the source, that is the exit flux of the source, how much flux I'm getting from the source. It depends upon also upon the orbital symmetry factor, how much symmetric it is, and also upon the basically the inelastic mean free path through which, I mean, basically if an electron is ejected, it should reach the detector directly. So if there is some other collisions, if there is some other inelastic collisions also, that also we should take into picture. And also it depends upon the analysis area, and also depend upon the analyzer transmission efficiency. So all three all together, it gives me the total. So the total intensity of the peak depends upon these factors. And so if we take them as overall, so and if we take them as an like the sensitivity factor, so the total the value of the concentration of the particular element can be calculated from the intensity value, and this concentration of the element gives us the parameter in which we can find out the concentration of the elements that are being present in the system. But with XPS, quote unquote, we should always understand the concentration of the element that we are finding is that we are finding are the surface concentration of the element. We cannot say anything about the bulk concentration. But obviously, if we compare vis-a-vis with some other tools like ICP-AES, ICP-OES, whatever, like some other analytical tools in which we can completely calculate the concentration of the element, then we can always affect, or and then we can always signify what is the surface concentration exactly from this spectroscopy. Okay. Another part is that relative sensitivity of the element. We can understand as we go along the Z line, as we go along the more and more Z line, as we increase the Z value of the element, the sensitivity of the element changes from S to P to D to 4D to 4F. For example, like if we are up till sodium, aluminum, we are almost in the regime of 1S. For the usual D elements and the other elements, it is 2P. From the yttrium, niobium, etc., it's mainly 3D, then so on and so forth. So basically, it's a more of a probabilistic understanding. So which orbital gives me the maximum efficiency, that is the maximum efficiency of ejecting the electron, we should take that orbital and we should calculate the quantitative or the qualitative aspects of from the XPS, checking that orbital into picture. I mean, we'll be getting the energy of the other orbitals too. And now, if the problem arises, if 2 or 3 elements together, like for in the same compound, if the 2 or 3 elements have the peaks in the same region, then they may overlap. And then in that juncture, we need to check the peaks of some other orbital actually. Okay, so another tool that comes into picture for XPS is we say is that depth profiling. Depth profiling is a phenomena in which we sputter the element with a particular ion, say a argon ion or a helium ion. We make a crater, we make a small hole there, and after making the hole, we take an XPS at a particular hole and at a particular crater. And once we try going deep, digging deep and deep, we continuously start taking the XPS and plot it as in a 3D model. For example, say we have a material of iron over which it is being corroded or it is being oxidized to form iron oxide. We can say like up till what layer the iron oxide is present from the XPS and from where the iron begins. Equivalently, like for example, we have a P-type or a N-type detector together, or a conductive SnO2, or 3 or 4 layers of elements together. We can say like up till which element and what is there with each, we can say the depth of that layer.
So Dr. Bhattacharya, sorry to interrupt. So like, is it different from LEIS, LEIS, low energy ion scattering, or it's?
So basically it's not exactly, I mean, it's not exactly.
Yeah, it is not electron. It is.
Yeah.
Yeah.
So here what we check is that here, I mean, if the element is like, I mean, for the basic fundamental here is that you hit the element within particular ion, and then you just dig a crater there and just take the XPS from there. And whatever you are telling is, I mean, there it's not an electronic technique.
Okay,
I mean,
okay,
other
okay.
technique.
Yeah.
But only difference here is that the sensitivity parameter. I mean, here we can work up till the limit of 5 nanometer. I mean, if the layer is lesser than 5 nanometer thick, depth profiling does. I mean, it's not good. So whereas the technique you came up with is a bit more sensitive than this. Does it answer your question?
Yeah. Thank you.
Okay, so another part comes into picture is called an angle resolved XPS. In angle resolved XPS, what we do is that we take into picture the format that if the electron is coming from the surface and if there is an angle from the surface, the exactly the intensity of the electron that is coming out is exactly not same. So taking that into picture, that is if I'm having a particular angle, so the sensitivity of the surface, or that the energy exactly of the electron that is moving out is exactly not exactly the same as that of the flat surface. So so if we have a curve, I mean, if we have a difference for that, we can understand from the angle result. So basically, like as I told you, like for example, if as we are doing a depth profiling for a oxidized surface, if we check the angle resolved XPS for that same surface also, we can generically understand like up till what depth we need to talk. Like, I mean, up till what depth we need to go. So you can give the ion energy accordingly. So it usually gives a generic understanding like how it is, how it's happening. Equivalently, the angle resolved XPS or the angle resolved UPS together, if we do it together, then we can exactly find out the valence band energy directly from this ER XPS and the ER UPS together. Okay, now let's take a generic XPS spectra into picture, and let's understand how it happens. So the system I have taken today for contention is it's manganese doped Fe3O4. This manganese doped Fe3O4, we have got different manganese doping in the Fe3O4 lattice, and we have tried to understand like we have done it initially stoichiometrically, and we try to understand like how much iron, manganese are there present as a function of doping. So as you can see, so here we are using an aluminum K alpha for the source. So you can check, like initially these peaks, whatever we are seeing here, they are basically Auger electron peaks, AES peaks as we say, and these peaks like Fe2P, this is the peak for iron. So as I was telling, XPS doesn't see any material as a compound. It always sees as a format of element. Okay. So for Fe3O4, if I check Fe3O4, Fe3O4 will be somewhere here. So we can check like that that iron Fe3O4 we get the Fe2PP and the oxygen peak, and for the doping of manganese we get the different manganese peaks also. We'll always be getting a carbon 1s inadvertently, and we get other peaks also which are not marked here. I mean the other orbitals for the iron, manganese, carbon or oxygen, all are there. So if we do a qualitative analysis, what we get is that if I do an almost 1% manganese doping, my surface has got almost like 1% doping. If I have 2, 3, 4, 5, like we get a good picture with this system. Similarly, as I was telling you, like if we take the individual peaks for the iron, and if we deconvolute it, as we know, Fe3O4 has got both iron +2 and iron +3, and being an inverse spinel structure, the iron +2 and iron +3 has got its particular octahedral and tetrahedral positions. So, so that can be understood from the the concentration of the Fe+2 and Fe+3 can be directly understood from the system, and we can see that as a function of Mn doping, the Fe+2 has a shift, whereas Fe+3 remains constant. So from this, definitely we can say that the upon doping of Mn, the Fe+2 is being altered or changed. Both its intensity and its position gets changed, whereas Fe+3 is not being touched with the Mn. Similarly, if we check the XP spectra for with the manganese, what we get is that the manganese is having only single oxidation state. Manganese is present as Mn+2 only. Manganese doesn't have any other oxidation state. And this Mn+2, if we check from the previous one, the manganese +2 is replacing the iron +2 for the process of doping. Now, equivalently, if we check the oxygen also, so basically for the oxygen, we'll be having for say Fe3O4. For the Fe3O4, we'll be having Fe3O4 means Fe3O4 can be correlated for the two lattice oxygens, and one basically the 529, 530, and 531.1. So basically, it can be correlated with the oxygen that is correlated to one Fe+2, one Fe+3, and another will be the hydroxyl group. Because in this system, in the Fe3O4 system, we can directly see, or we can check, there are no oxygen vacancies present. So that is quite pertinent from here. So and equivalently, once we dope with the manganese, there's one more peak with the manganese oxygen also. So we'll be having a oxygen being attached to Fe+2, Fe+3, and Mn+2. Similarly, if we check the element, this system, what we did was the urinal adsorption upon this system. That is the Fe3O4 system. We have checked the urinal adsorption on this element of Fe3O4 system, and what we found was that uranyl ion was exactly post adsorption. I mean the amount of absorption of the uranyl ion was very meager, so it was in the almost in the ppm level, and the means the efficiency of XPS is in the PPT, that's parts per thousand limit. So we cannot see uranium there, but how the uranium has interacted with the manganese or iron, that we can see from iron and manganese. So what we see is that the uranyl ion directly interacts with the Fe+2 system, and in the manganese dope system, it directly interacts with the Mn+2 system. So once we did our if we take the picture, if we do a theoretical understanding, if we do a theoretical calculation, also we find that the uranyl interaction with the manganese is that is the manganese which has replaced the octahedral one is the least one, and also the octahedral it goes with the Fe+2. You can check the Fe+2 is the octahedral one, and Fe+3 is the tetrahedral one. So so the uranyl interaction is least with the manganese Mn+2, and also least with the Fe+2 system. Okay, so we come to a picture like this, that here the uranyl ion usually is getting absorbed or is mainly interacting with the Fe+2 system in the Fe3O4, and if there is a manganese dope in the Fe3O4 system, this uranyl ion directly interacts with the Mn+2. Okay, so for doing this short theory, we have taken one consideration or one presumption that obviously it is in solvated region, because the adsorption occurs in the solvated part. So we have taken for this calculation supposition that the particular solvation energy is constant for everything, because if we need to connect to the XPS, it's under a vacuum technique. So we have taken the solvation part to be constant. Post taking the solvation part to be constant, the ionic interaction or the electronic interaction of the uranyl ion with the Mn doped surface and the Fe3O4 surface, that is, we have taken an Fe3O4 311 surface, and we have calculated the energy. We find that whatever we find experimentally, what we see from our XPS2 can be directly evidenced from the theoretical model also. Okay, so now up till now I have tried to make you understand about the about what we get from the XPS. Now let us understand a bit about the instrumentation for the XPS system. As we have told that it requires initially soft X-rays, not very hard X-rays. It requires a soft X-rays, and it requires very ultra high vacuum. Very high vacuum is required for the system. So why do we require it? First of all, we need to understand what's like what we call for a vacuum.
Dr. Kostov, sorry to interrupt. I mean, we have like around 7 to 10 minutes more. Is it fine for you, or it is less?
Can I get 10 minutes more? Is that?
Yeah, 10 minutes, please. 10 minutes is fine. Thank you. Thank you.
You'll take 10 minutes more and wrap it up. Okay.
Thank you. Thank you.
Okay, fine. So if we have an vacuum, it can be differentiated into like UHV, low vacuum, medium vacuum, or high vacuum. So ultra high vacuum is almost in the regime of 10 to minus 11 torr vacuum, we are saying. So if the students are around, can I ask a small question to them? What is your idea about vacuum? What do you think? In vacuum, there are any molecules or there are no molecules?
So students, Lakshmi, are you there? Lakshmi, what do you think is a vacuum? Or Sonam, are you there? Hello, you can unmute yourself. Are you? You can unmute yourself. Hello, is anybody there?
Yes, sir.
Yeah, Bolo. So what do you think about what is your idea about vacuum? Are there molecules in vacuum or no molecules in vacuum?
Sir, vacuum is like space of matter.
No, we you know, I taught you TEM, SEM, all that. So
Yes,
why
sir.
do we need vacuum there? So that the electron beam does not do what? Does not
Scatter, sir.
scatter. What will the scattering will do to? Scattering किसके लिए होगा?
The molecules.
Molecules. So what is your answer to sir's question then? So are there molecules or no molecules, or there are less number of molecules?
There are less number of molecules.
Yeah, that's a very correct answer. There are much lesser number of molecules. So basically, if we check in the NTP, so I mean, if I take 1 atmosphere, it will be having 10 to the minus 20 the Avogadro number of molecules, right? So if I'm having a vacuum of 10 to the minus 11, so it will be having 10 to the minus 23 minus 11. That is that many number of molecules there, correct? So now the question comes: why do we require such a high vacuum? So as we are measuring the kinetic energy of an electron that is being ejected, so that electron should reach the detector directly from the sample, right? So it should be its fast mean free path. It should be within its fast mean free path. So if it is not within its fast mean free path, then it will be colliding with different materials, and then the kinetic energy that we will be measuring will be erroneous. So so basically, then the lesser the molecules that is required, the present, that is better. Now the thing is that, like, if we measure for the fast mean free path for all the moieties, what we have is that the beryllium has the maximum energy required for the mean free path. Still there, we require a vacuum of 10 to the minus 7 torr, not 10 to the minus 11 torr. But we still require a stronger vacuum in XPS because of another factor, which is we call as sticking coefficient. What happens is that if we think of an atomistically clean moiety, that is atomistically clean surface, then in the atmosphere, there are basically nitrogen, oxygen, and moisture mainly. Others I can disregard. And so if it's in a smaller amount, the smaller moiety will be much lesser. So what happens is that the sticking coefficient of oxygen is very high. So what happens is that oxygen start building monolayer after monolayer upon the surface, and as it forms a stronger monolayer, for example, if I'm checking for silver, I'll be checking and getting an extra false peak of oxygen just for the sticking coefficient of oxygen. So we go to a much stronger vacuum so that we get a window in which these monolayers cannot form. So that's the reason we have a very high or strong vacuum there. Okay, basically the detector in an XPS is a statical electricity detector, where we have if I give a very easy picture of it, we have basically it looks like an hemisphere, and there we have two copper plates and a gold plate in between, and all these plates, these two copper plates, are being biased. So if they are biased, we overall know the electric field present there. And the gold plate will be such that it is completely unbiased. That is, the value of that biasing will be completely zero. So you know that exact unbiasing position. And so if I know exactly from where the electron is coming and I know the theta, so I can calculate the energy of that electron at every point. And what is done is that this energy is being divided into smaller channels. So whichever channel it takes and the energy, it gives me the exact value of that particular energy, and I can calculate the kinetic energy of that moiety. The source, as I have told, the source we usually take is aluminum K alpha and magnesium K alpha. So as we can understand, and in the XPS, what we do is we deconvolute the peak and try to find the oxidation state, or that DOS, that is the density of state from that. So my source should be such that I can do the deconvolution, and the different amount of deconvolution is in the regime of 0.1, 0.2, 0.3 volt. So the line width of my access source should not be more than 1 electron volt. So that's the reason we choose electron and magnesium K alpha, where you can see the line width of aluminum and magnesium is 0.85 and 0.7. So if we require things where the resolution is much strong, resolution is requires much higher, we'll be more of using the magnesium K alpha source. If we require somewhere like where the intensity needs to have higher energy, we use the aluminum K alpha source. Apart from that, apart from these different lab sources, you can also use synchrotron as a source always, where we can tune the X-ray energy. Okay, this already I can skip. So this is how a dual anode X-ray source looks. So there are two anodes. They are cooled by the water. There is a separator there, and one at a time is being. I get the electron from particular anode, and I start getting the XPS fluency. Okay, so equivalently, there's a monochromator. We use a Roland circle for the monochromator, for the process of monochromatization, where we use the Bragg's principle and use basically a quartz crystal, that is a silicon 11110 crystal as a disperser. By the Bragg's law, that from the different guards of the source, only one lambda can do the Bragg, can have the Bragg operation, and we take that as that particular lambda as for the monochromatization process. Okay, so So basically, this is how the XPS system should look. We have a X-ray source. If we require monochromatization, we have a monochromator, we have a sample, and we have a detector. Okay, and okay. So now, if we think of that, there are another thing that is called a charge compensating tool. What it does is that if we know my surface is charged, either we can open this charge compensating tool, either to give some electron or to take away some electron. I mean, it usually gives only electron. Like for example, there are several polymeric materials which are not sensitive to XPS at all. For that, we require this tool to imbibe some charge so that we start getting electron. And if the surface is overcharged, say we have a charging of almost say 3 or 4 electron volts, we give a compensation, a charge compensation, so that we have a proper value of the binding energy. Okay, so this is my tool in my lab. So here you have a dual anode source. We can do Auger electron spectroscopy. We can do angular Excel spectroscopy. We have a scanning electron microscope. We have a scanning Auger microscope. We can do depth profiling. We can do in situ reactions in a cell, and we can take the XPS. We can do an ion scattering spectroscopy. Ion scattering spectroscopy in one line is something like Rutherford backscattering, where we use the smaller, we use ions with lower energy. We use ions in the energy of in the keV for 0 to 5 keV regime. And if the ion basically, as we understand, in the XPS, what we are doing, we are measuring the kinetic energy of the electron. So if we are measuring the kinetic energy of an electron, if we change the polarity of this detector, we can measure the kinetic energy of the ions also. So as we can measure the kinetic energy of these ions, if it does inelastic scattering, as the ions are much heavier than the electrons, we can measure the how it interacts with the surface. So this ISS is far more surface sensitive. It gives the value or gives the results up to 2 nanometer rather than 5 nanometer. So the different surface analysis tools, as we know UPS, XPS, UPS. We have AES, we have EELS, we have SIMS, we have neutral mass spectrometry, and we have ion scattering spectroscopy. We can also do XENS. So now some examples. Initially this so say we have a core shell material, and if the Z is very nearby, like for example, if the Z is very nearby for gold and platinum, so both SEM and TM usually gives us near. Problem is that if the Z value is very nearby, identifying exactly the core shell with the SEM or TM becomes a tougher thing. Here XPS can play a stronger role. Here if we do a sputtering and XPS together, what we find is that initially as the gut of the XPS is a bit stronger, initially the shell gives me the XPS spectra, and once we do a sputtering in, after some sputtering time, I get the spectra of the core also. So the amount of sputtering that is required from where I start getting the spectra of the core can suggest me like how the core shell is being produced. So this type of understanding is very strongly done for the closed Z elements. Here we did for a gold and platinum together. Here you can see post sputtering, that is, it was a gold core and a platinum shell. Platinum is almost constant as a function of scattering, but however, the gold, as it is a core, as a function of sputtering, its intensity is increasing. So we can check and if you check the SEM or the TM, it's very tough to tell about this type of core shell. Here, and the XPS can be strongly utilized. Another thing, if you want to check the here what we did here, it's a pyrochlore structure. It is Y2Z2O7. This basically it is Y2SN2O7 in which zirconia has been doped in the tin side. So this structure, what we did is that we tried to understand basically if we dope zirconia in Y2SN2O7 is a pyrochlore, whereas Y2Z2O7 is having a fluoride structure. We try to understand the order disorderness of the system. It's tough to do from the XPS, but we're quite lucky to do that. So as you can understand that Y2SN2O7, it is a pyrochlore structure. It's a complete pyrochlore structure. So it will be for a pyrochlore, the coordination value so it's a A2B2O7. So for A, the coordination number is 8. For the B, the coordination number is 6. So basically it's a cubic and octahedral system being present. And the total number of oxygen presents are of two types. One is a 48F and then 3B. So 48F is basically having 2 T9s and 2 yttrians plus 3, whereas the 8B will be having 4 yttria plus 3. So there is definitely difference in binding energy. So there are two, we can get two different types of oxygen here that you can see. But as we dope zirconia, what happens is that it goes from exactly pyrochloride to a fluoride. So a fluoride has gotten coordination number of both A and B will be having a same equivalent coordination number of 7, and neither. So basically the coordination number of B increases and A decreases, and thereby the quantity of these, the charge difference or the difference between the binding energy of these two oxygen atoms also nullifies, and their intensity decreases. That we exactly get from there. Also in the, if we take the XPS of the zirconia, what we find is that there is a strong shift, because for zirconia, its coordination number increases. As the coordination number increases, the oxygen around the zirconia increases. So if the oxygen around zirconia increases, it pulls the electron more from the zirconia, the oxygen being more electronegative. So the binding energy around the zirconia also increases. So definitely we can show that the order disorder structure from the XPS parameter. Okay, I tried to understand one small doping thing from the XPS. So we can just skip it. So basically what we think of in doping is that if we dope in a structure, for example, if we dope an MH plus in the titanium structure, what it can do is that either it can replace the titanium 4 plus and dope there, or it can go to the interstitial, or it can form as either it can be a substitutional doping or it can be an interstitial doping. Now it depends upon the charge of the dopant. Like it has to maintain the overall lattice charge. In order to do that, it can create some anionic vacancy or an cationic vacancy depending upon the type of doping we're doing. Okay, so in order to, I'll take one more example at least. So what we tried to do was we tried to reduce, photocatalytically we tried to reduce carbon dioxide to produce methane. It's another source of energy production, like apart from water splitting. What we do is that we reduce CO2 to CH4 without using any hydrogen source, in the presence of using sunlight and using moisture to reduce the CO2. Okay, so what we find is that upon doping copper in the titanium, the lower the amount of doping, the more amount of methane was being produced. So if we check the overall the textile parameters, we find that as a function of doping, as a function of copper doping, the band gap obviously goes from 3.2 to 2.5. However, the production of methane, but the production of methane was the other way around. So copper 1 has got more amount of methane produced rather than copper 10. So we try to understand why that was happening. So if we check the XRD parameter of it, we find is that, so what we are doing, we are doping copper in the titanium system. If you are doping copper in the titanium system, copper is in either +1 or +2 state. Titanium is in +4 state. What will envisage is that also the copper, so basically CuO will be means longer in length rather than Ti4 + O, right? So therefore, if we dope copper, what will envisage is that we'll think that the lattice will increase. However, whatever we check, we found out is that the lattice volume decreased. So what we basically, that can only happen if there is any vacancy. So overall, there is a definite amount of oxygen vacancy they are being produced in the system. And also if we check copper, so the oxidation state of copper was present in the form of copper +1 and copper +2. So in the lower concentration of the copper +1 concentration was higher, and post photocatalytic process, that post photocatalytic reduction, we can see that the concentration of copper +1 has strongly reduced. So we see that the copper +1 is more of utilized for reducing the CO2. And equivalently, in the oxygen, we get the oxygen vacancy also. that we have seen. So this is surface oxygen vacancy. From XRD, whatever we have found is the bulk oxygen vacancy. So so we also see that as a function of photocatalytic reduction, the oxygen vacancy also decreases. So so what we find out is that if we correlate the copper plus and the oxygen vacancy together as a formation of methane formation, we can definitely say that the more the amount of copper plus one and the oxygen vacancy that is present in the system, the better photocatalytically active that system is. So we try with another system where we do an oxidation system. Here we have doped vanadium and the titanium system, and we have tried to oxidize ethylene. What we find is that up till so here what we find is that the titania after a particular doping, that is after post 5% up till 5% doping of vanadium, titania is present in titania plus 4. But if we dope more than 5.8% of vanadium, we find that titania is present in both plus 3 and plus 4. So what happens is, so vanadium is basically present in two oxidation states, plus 5 and plus 4. Here titania, if the amount of vanadium 5 plus increases, the titania, it's to maintain the lattice charge, more amount of titanium 3 plus is being produced in the structure. Now, if it is an oxidation process, titanium plus 3 eats away the whole very fast and reduces the reaction. So we can prove directly that if there is a formation of titanium 3 plus structurally, that reduces its photocatalytic efficiency. So I'll skip that and I'll complete it here. Thank you.
Thank you so much, Dr. Bhattacharya. I mean, it was really, it was a very enlightening talk actually, because, you talked about the basics of XPS and your experimental results. So, I mean, are there any?
It was a great work. In fact, he I mean, just gave a detailed information.
Yeah. I mean, if you would be associated with Dr. Kostov, you would know he's a meticulous person. I mean, several of our papers, I mean, I take his advice, and he's co-authors on many of my papers, and he's a very meticulous person.
He's working on solar, this one.
Water splitting, hydrogen production, catalysis. Yeah, he's the catalysis person.
My field of research is my field of research is several. We work basically on the catalysis field of catalysis. We try to understand the mechanistic aspect of all the catalysis. So I've got several in situ reactions. I have an in situ FTR to understand the different intermediates that are being produced. I have in situ XPS to understand how the surface acts. We work in the field of in situ exapts to check like how it is working. Apart from the mechanism, I work definitely in the field of energy. Like my field of energy is CO2 reduction, mainly CO2 reduction to methane. We work in the field of excess splitting, and apart from that, I definitely work in the field of surface along with the XPS.
Dr. Kostov, my field is not related to this, so I just wanted for a piece of information that what is the status of energy production in the area of carbon dioxide, and this, I mean, what the percentage of energy is being produced by using these non-conventional methods?
Okay, ma'am, that's a very nice question. Actually, today's day world, it's going to be the world of renewable sources now. So I'll just give you a simple table to understand. So for example, if I'm using water splitting, so hydrogen obviously is the best fuel we can have, because 1 mole of hydrogen gives me almost 141, not 1 mole, 1 gram of hydrogen almost gives me 141.
Mute.
You're muted, Dr. Bhattacharya. Dr. Bhattacharya, you're. Hello.
I think there is some.
I think we are exceeding with time. That's why these problems are coming.
Hello. Yeah. Now, yeah. You're audible.
Okay, fine. Sorry about it. Some problem in my home for the internet. So basically, we cannot beat the solar economy factor with the hydrogen, but you can understand basically if I'm making a methane, it's almost an 8 electron reaction. If it's an 8 electron reaction, obviously the quantum efficiency of the process is much higher as compared to that of a hydrogen reduction reaction. And equivalently, for production of hydrogen, we will be requiring a new grid. So all over the world, we require altogether a new grid. But see, methane is today being used everywhere, like a CNG car or a person which is using LPG. all are nothing but methane. So already we have a grid. So that way, checking out that problem is easier with CO2 reduction. And overall production, I mean, today's day, if we can utilize the CO2, which is taken as a bad moiety, if we can use it for production of energy or even for valorization, I think that's a very strong and economically strong tool. So today's date, what it is being understood, it is being tried to be coupled with biomass and also tried to be coupled with H2O together.
Okay.
Thank you. So, Madam, can I propose the vote of thanks? Or Madam, do we have something else?
No, you please go ahead.
Yeah.
And actually, it was a very informative session.
Yeah, it was very good. So with the blessings of our founder president and on behalf of the chancellor and vice chancellor and pro vice chancellor of Amity University, I thank Dr. Kaustav Bhattacharya and Dr. Kashinath Ojha for giving us such enlightening talks. And we hope that we will collaborate in the future too. And we will have some, enlightening sessions too. So, and I also thank the IT team and the entire CBFS department for organizing such a wonderful talk. Thank you.
Thank you. Thanks from my side also. Thanks, Anirban, for Coleman's for inviting me to present a talk, and thanks to your Amity University also for giving me a platform for presenting my this talk of mine. Thanks from my
I
side.
think my students are being benefited, and I thank all of them for attending this session online. And be connected with the Dr. Kaustav, and he will give you lots of knowledge. Thanks you, Dr. Anirban, for calling the speakers, best speakers. Thank you very much.
Thank you, madam.
Thank you all. I think Vivek, can we close it now? Please close it.
Thank you. I'll check your leave. Bye.
Yeah, thank you. Thank you. Yes.